And basically, yeah.
No.
Muted.
No, I didn't connect. It's muted.
Count?
Yeah.
Yeah. We just share the presentation again. Thank you. So the workshop today is connected closely to objectives of the work package 2, which are to transfer knowledge and expertise to Biosense from our partners and to support researchers from Biosense in, for example, habitat modeling. And if you remember, in November, we had the part 1 of this workshop organized online by Jose and Borja, in which we covered the first steps in data collection for habitat modeling. And now that workshop covered mostly in situ data collection. Now we will talk a little bit about remote sensing data collection, which will be, the presentation will be given by Anna. And then we will go sort of a step forward into what comes next, which is the data curation and other important processes. And why are we doing this? Can we go to slide number 4? Please stop
moving.
One second. No. This way? No.
Maybe no, it doesn't work that way.
Okay, we'll take care of it. Anyway, the entire point of Sonata is to boost Biosense into a regional leader in providing data for habitat modeling. There we go. Thank you. For habitat modeling and developing biodiversity and climate indicators for assessing the state of ecosystem and the future natural capital accounting. And on the other hand, we are doing all of this to prepare for the implementation of nature-based solutions. So we want to accelerate the institute to be the leader in the setup of nature-based solutions in the future by providing different kinds of services to all land use actors in Vojvodina for starters, but then we want to think wider for Serbia and the Southeastern Europe. And okay, that's it for me. Jose, do you want to say a few words?
Yeah, just to sum up, to recap a little bit what we talked in the first part of this workshop. That workshop was more, let's say, theoretical. We had online and different presentations, 3 presentations, on which Borja and me told about why do we need in situ data for this biodiversity assessment or this habitat mapping, landscape mapping, and so on. I don't know if many of you are related with this data collection, with this biodiversity information in the field. And I would like to know if, do you know, have you ever been in the field collecting information for anything that has to do with biodiversity? I mean, it's important, it's easy to understand, but it's important, as we discussed yesterday, it's important to really to have been there collecting that data, because it's a huge effort. When you are there and you know what you're talking about, you realize that you need quite a lot of time for collecting information from the whole territory for the different gradients. That information changes over time. So data collection is quite is quite time demanding, but a lot of effort, a lot of knowledge. And when we have that data on the table, we start to work in modeling. So all of you have worked with remote sensing, or do you know a little bit of that? With the spatial modeling, do you know that somebody's new in remote sensing, new in spatial modeling from here? More or less? Okay. Well, so what we tried to do in the previous workshop was to explain the importance of in situ data, even though you have never been there, but how important is in situ data for this, in this particular case, habitat mapping, but environmental modeling exercises. We always start from the knowledge that we have on the field. So this is the point 0, and then we start working with the spatial data, remote sensing, and so on. So what we did in that first workshop and what we will keep on going during the whole Sonata project from our side is to be like there with, come on, in situ data. Let's reduce the uncertainties. Let's analyze which information can we get from the in situ data for afterwards extrapolate with these spatial tools. And today the objective is to, we decided to spend 2 of the 4 presentations in remote sensing, because we want to eliminate like some feeling that we found during our career in many places working with stakeholders and so on, that remote sensing is just click and then load them a picture. And that picture is magic, it's cool, it's really...
Image.
No, that picture is nice and easy to get and cool, so it's everything. So in situ data disappears somehow, and not only disappears in situ data, but disappears everything that has to do with the quality of that image that you have to actually combine. That's what I'm going to jump into in my presentation. The combination of the effort of in situ data and the effort in managing properly the image with cloud computing and these very cool capabilities that we have now. We are going to show you briefly Google Earth Engine. This is the tool that we use in the project. Our colleagues from Vito will use OpenEO workflows to operationalize and to make this combination of in situ plus remote sensing and modeling available to reach at a large scale to the whole Serbia or Vojvodina, I don't mind. But what we want to do here, we decided to do in a very basic level to discuss. Stop us at any point. Let's give your opinion, or I didn't understand this, I want to know more about this. Because the objective of today is not just give you blah, 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 like the last day, that were important of how sampling information, the units, habitat types. So we have already in situ data. Theoretically, we are going to have in the coming months. We had yesterday a very good discussion that will end up with a good pipeline protocol to collect in situ data. Once we have the in situ data, what we want to tell you in this workshop is how that in situ data need to be, the word we use is data curation. So that data need to be coupled, put together with the remote sensing before the modeling. So both worlds need to talk the same language. In situ information gives you information. Remote sensing gives you information. So in situ, we apply expert knowledge, spend time and effort managing the in situ. We have to spend time and knowledge managing the remote sensing. If somebody here is expert in remote sensing, it's obvious what we are going to tell, data corrections, time series, and so on. And I will start with the basics of remote sensing and things that you can forgive in remote sensing, correction, and so on. And then we will put together both words. Then Gonzalo is gonna show us Google Earth Engine to allow all of you to have an account, to log in Google Earth Engine. We have couple of scripts to give you a couple of examples to run analysis. And Google Earth Engine, from our view, is like, let's make it easy how managing the images and remote sensing. And then we put together remote sensing plus in situ to start modeling the modeling part. Okay. At the end of the workshop, Jetse Stoorvogel is Jetse here. It was my supervisor of my PhD. Will talk about the same thing, but instead of habitat mapping of vegetal biodiversity, on digital soil mapping, on how extrapolating the in situ information from soil into large scale mapping to give an overview. So I stop. So remote sensing needs to be treated as a science, and Anna will show why and how.
And just one practical information. I sent email, sorry, Anna, with the access to folder with the material for today. But we had some issues with the SharePoint, so I will send in a few minutes a new email with a new link that will follow.
Yeah, sorry.
Well, first, I have to apologize for those of you that they're experiencing remote sensing, because most likely what I'm going to say is far too basic. But we wanted to make sure that everything was covered, like the whole picture, and strengthening those aspects that need to be very much taken care of. Because the quality of the data, it depends on them.
Is this the one?
Yes. Yeah. So, well, basically, I mean, the objectives that we were thinking about was like, well, what do we want from this talk? Is like to make sure that for those of you who are not experienced in remote sensing and understand which data products have to be used for habitat mapping. Also to make sure that practice are being followed in a very rigorous way in order to obtain and process the remote sensing data that we are going to use afterwards with the
Sorry. Ethan. Okay.
Jose,
Sorry.
you're hijacking. And then we'll just to build the skills in image processing, like using, I don't know, this is just an example, using smart software. And the learning outcomes that we were thinking, well, first of all, yeah, for those of you, for those of you who are not familiar with remote sensing, to gain knowledge about the remote sensing data products, to gain knowledge as well on the processing chain of the imagery, and that a bit. So we're going to start from the very beginning. So in terms, well, what is the Earth observation, right? Like, what do we understand by that? What we do? I mean, there are different types. Jose.
Oh.
It is Jose. Very nice, eh?
How can it be possible?
He's my friend, even if he hasn't appeared. So there are many types of remote sensing, obviously. Like there are the drones and there are the cameras, but there are also as well the satellites, and those are the ones in which we're going to focus in this talk. But basically, I mean, it's just the same. I mean, it's acquiring information from a distance and not in touch with the target that we are observing. So, as you all know, I mean, the sensors have different characteristics that are going to change in function of the platform altitude. So, for example, the spatial resolution is going to be compromised by the platform altitude, and there are also by spatial resolution, I must say, that is the size of the pixel. So, I mean, these are like very basics. And so focusing on the optical remote sensing, because as I said, I mean, there are different types and different sensors, and there's a whole bunch of things that can be done under the umbrella of remote sensing. But focusing on optical remote sensing, what we obtain basically is just an image of the radiation that is that comes from the Earth's surface. So, and that radiation basically comes from the illumination of the sun, blah blah, and what we get is spectral information. So it's information in different wavelengths of the electromagnetic range. So in function of the type of sensor that we deal with. Like we are gonna get information from different types of information based on the organization of where those spectral bands are located in the spectrum. So not all sensors are usable for all sorts of things, because I mean the information that they can have, that they can bring us, they might not be the adequate one. So that's something that we have to bear in mind. So just as a sum up, basically what we get is that cube, like this cube of information that basically are just a pile of metrics, like referring to the spectral bands. Right? There's also the difference between hyperspectral and multispectral. So basically, the main difference is the number of wavebands that we have. So the hyperspectral covers in a very detailed manner this spectrum. So we have normally the hyperspectral, they have more than 60 bands, spectral bands, whereas multispectral, they can range up to 25, 30, but it's not the usual thing. And basically for habitat mapping, the type of sensors that we're going to use, we're lucky if we get the 10 bands. So the information is very concealed in very specific bands. And then there's the other one, the other type of optical sensor is the LiDAR. And this is this source of information. We Gonzalo and Jose, they're very much experts, and they apply it to habitat mapping because it gives us the information about the vegetation height and it provides us with the digital elevation models and in a very accurate way. So in terms of the habitat mapping, this source of information is really amazing. But the drawback is that normally, it's installed in planes. So basically, for example, in Spain, we have it. It's just every, I don't know how many years, like every 5 years we get a flight all over Spain, and so, but this is not very common. So let's get more into detail, and basically what we're going to use for the habitat mapping, or whatever the modeling that we're using, are going to be the spectral signatures. The spectral signatures basically is just the outcome of that data cube that we had that I showed you at the beginning, and per pixel is the signature of the target or the surface that we're observing. So it measures the quantitative measurement of the spectral properties of the object that we are observing. So this spectral behavior is like the DNA of the surface, and is what allows us to discriminate between different targets. Sorry, because I didn't realize that I put this graph is in Spanish. Sorry, but you can see here the differences in spectral behavior. Like for example, this is sandy soil, a typical vegetation, signature, water with a lot of turbidity, like suspended matter, and the clear waters. So you can see the obvious differences along the spectrum. So this is just an example of the type of things that we use for the habitat mapping. And basically, these are the signatures that we get from very specific habitats. Like, well, these are what we call the end members. What they do is that they sum up. They are the average behavior. Like what we obtain from them, so we can get the average behavior of a habitat or a land cover or whatever, right? And well, this is just, I mean, these are just an example of how they look. How do they look in using a hyperspectral sensor? This is from field campaigns that we do. And another thing that we have to bear in mind, and that's related to the spectral behavior, is that the cover, the land cover, or the habitat is not going to behave in the same way along the year. So there's the spectral phenology, and that's something that is really useful in order to characterize what we are observing to, because at certain point, habitats, I mean, for example, I don't know, like how many of you have opened an image and from a certain moment and they have found, I don't know, like a very much, like the similarities, like there are not many differences between, I don't know, different pastures or crops or whatever. But those differences, they might be more, it would be easier to observe them at very specific moments along the year. And that's something that it helps us in order to discriminate the types of habitats that we're observing or that we want to. Okay, so, well, this is like a really obvious question. And again, I'm sorry if this is really too basic, but I just want to make sure, why do we use satellites? Because, well, first of all, because they allow us to monitor, in a very strict way, because we have routine observations, data acquired at the same, in wide areas, at the in the very same manner, so it's compatible. And basically, this is, it complements as well the in situ sampling. So we have to go together with the in situ data in order to make sure that we are understanding what we are observing. And then this seems obvious, but many years ago it was not. The data is free and open access. So that's something that is important when you have no information and you have a limited budget and you want to know what is happening there. You can use remote sensing for observing. So, if we go a step further, let's jump into the Copernicus program. this is just, it's a madness program. But basically, I'm sure that all of you, they know about it, and they have been, at a certain point, they have been in contact with it. But it is just unbelievable how fussy and difficult it is to get into it and to understand what data is about. But basically, I mean, the Copernicus program is the Earth observation, the European Earth observation program, right? And it's focused on users. So it's not a program oriented or exclusively oriented to researchers. This is quite a bit of a change from what it was like some decades ago, that all the missions that were released, they were very much oriented towards military or researchers. But in this case, it's very much focused into users. So that's why it provides, it makes sure that it provides free and open access data. And it has different services, information services, okay, that combine as well the in situ or the non-space data, modeling and so on. So, the program is coordinated and managed by the European Commission and is implemented in partnership with many European entities like, the European Space Agency or the meteorological, the EUMETSAT, that is responsible, for example, Meteosat or whatever. It's CMWF. It's mostly linked to climate or the EU agency, the European Environmental Agency, Anyway, well, the questions that we might ask is why? And why is all this happening, right? So what I was saying is like before, the program wants to monitor variables to understand and manage the environment in an adequate way. This is something that we discussed. We had a bit of a discussion, I don't know if it was yesterday or the previous day, about the differences that each country, when it has to report, every European country has to report every 6 years, but the difference is report the status, for example, of the habitats, right? So the difference in the methodology used, the data use, and so on, makes them very difficult to be compared. So this is something, this program, what it tries is to make sure that the people can report using remote sensing or satellite and modeling and in situ and so on. So that's something that is homogeneous for the whole Europe, and it's not like talking like pears and apples, right? That in some of for some countries, I don't know, for example, the definition, I don't know how many years ago, person told me I don't know, I'm in this meeting and the concept that they have about the forest, it varies if you're in Spain, in France, in Poland or in Italy. That concept is something that it has to be, what we are reporting is different in the different countries. So basically with this, what we do is we have a tool for reporting. We obtain the continuous measurements in space and time. For that, there are this constellation of satellites, or family of satellites that Copernicus has. And one of the things that it was extremely important for the European Commission was that it had to be operational and reliable. And that's why it's oriented to the user. So that means that it has to be validated, the quality has to be warranted, and it has to be a robust service. So, and for that, what they do is that they deliver a bunch of, I have written the easy variables, but it's not that they're easy, that they are more straightforward than other variables to be reported, and they make use of their own satellite system. But there's something that it has to be, well, bear in mind is that not everything can be measured by remote sensing. That's where the In Situ data jumps into the equation as a strong pillar. So the Copernicus program, as I was saying, I mean, it has these 6 main services: the atmosphere, marine, land, climate change, security, and emergencies. They provide loads and loads of data, and that's something that I would recommend you to log in and just browse around the different products. So, but the 2 main services that they are of use for, that they can be relevant for SONATA are Copernicus the Copernicus Climate Change Service. That obviously, I mean, with that name, what we get is historical data and projections of climate change. We have essential climate variables, like temperature, precipitation, sun moisture, solar radiation, so on, and climate indices. These things, I mean, this service, what it has, I mean, the products that we get from this service, they are not very detailed, in the sense that the resolution is relatively coarse. So, but, well, they're related to the climate scales, that they are not that detailed. But so I'm saying this because the difference with the Copernicus Land Monitoring Service, that it has also some of the variables that are included in the Copernicus Climate Change Service, is that data has a spatial resolution that is more refined, and it gets adapted to the differences in the terrain and the landscape and so on. So this is really, I mean, it's a useful source of information. Now this is just, I'm not going to spend this because this is just a mess of the Copernicus program, and that is divided into the service and the space component, and each thing has its own different groups and so on. It's a really complex ecosystem. So the Copernicus, what I was saying, like the satellites of that come from that have been designed within the Copernicus program are the sentinels of the environment. There were that was the original idea, and but as well, they also have all sorts of contributing missions, like I don't know, Landsat, for example, and Spot, and other missions that are from different sources outside ESA. And it has to be clear that satellite images are not exactly the Copernicus services. I mean, they are part of them, but they are not strictly the same. Well, this is the ton. These are the ton of families that we get, but for the habitat mapping, the most recommended one is the Sentinel-2 because of the size, the pixel size. So in terms of the data processing, it's important to know where the images, what's the transit of the images. So far as the data is the data acquisition by sensor, then you have the processing at the ground base. So there's the conversion of the energy that is received by the sensor into the images and into something that it is meaningful. And then you have the analysis, both quantitative and qualitative of the data, and the accuracy assessment. So for that, there's a bunch of radiometric, geometric corrections and reprocessing every odd years. It depends on the mission and the degradation of the sensor and so on. And then there's the distribution of the information to the users. And that distribution comes in, in different levels. There's the level 0. This is a level that is not actually, right now, it is not distributed or not on the Copernicus data. But for example, when you're using a drone or when you're using an urban sensor, what you're going to get, the first thing that you're going to get is the level 0, the raw instrument data that has to be converted into level 1. That's the standard. I mean, there are different types of level 1, but basically the standard product that the user receives is the geolocated and the calibrated data. Then you have the level 2, which are the geophysical variables derived from that level 1 product, right? So these are corrected, the atmospherically corrected, and they are supposed to be more accurate. And then you have these weird level 3. The level 3 is basically a combination. It's a spatial, it can be many things actually understood by level 3, but basically what it is either you take a bunch of images from the same location and you perform an average, for example, I don't know, monthly average or a yearly average, and that would be a level 3. But technically speaking, that level 3 will include as well the mosaicing of a bigger area. So it's just basically you have all these bunch of scenes that they are regraded, that they are averaged into different, it can be monthly, 8 days. It depends on the, or seasonal, yearly, or whatever. And then the last one is the level 4. The level 4 is the easiest one to get. Like it is the level of data that requires less knowledge, in the sense that you get the data, you get the information, and that's it. I mean, you can plug it into your model and it will be fine. Because this is a combination of modeling and level 3, and so it's a far more complex. So in terms of production, this is the most complex step, but for the user is the most easy. So these are basically, for that, I mean, you need greater skills. The lower the level, you need greater skills. And if you go down, so the first thing that it has to be, this is really paramount, is the atmospheric correction. Because what the atmosphere does is, the sensor, what it gets is the radiation that comes from the surface, but not only from the surface, but the atmosphere, and something that is 800 kilometers away. It has a lot of room for interference, right? So what we have to, what is really paramount is to correct that influence or that noise coming from the atmosphere. And this is, for example, an example that I think is very eloquent, and I really like it, because this is how this signal varies and function is exactly the same target, but acquired at different altitudes. With the sensor at different altitudes. So you can see perfectly well how the spectral signature is perturbed. So the only problem with this is that basically, to tackle the atmospheric correction is an assumption. You have to, and there are different approaches to do them. The most reliable ones are the ones that are really models, not maybe you have heard of the dark pixel approximation. So you get an image and then you go for the reflectance of the darkest pixel of the whole image, and then just extract it all, assuming that darkest pixel, what is a reflection of just the atmosphere. It's more complicated than that. So, the problem of using the different models is that not all the models perform in the same way. Depending on the target that we're observing and that we are monitoring, the models are more accurate and more reliable than others. So, this is just an example of what we get. In a sensor, this is the spectral signature of a coming from a sensor located at 300 meters. This is the top of the atmosphere, so it would be what the sensor is collecting at that very instant, and you see what is the influence from that signal. All of this comes from the atmosphere. And then, in this case, this is for the water. This is It's a complex target because it has, as you can see, I mean, the signal is very small. But then what you obtain, for example, once that you retrieve the atmospheric correction, you get the surface, the at-surface signal. But if you see at the green light, the green curve, we can see that it's a bit different from the water leaving reflectance. Why? Because of the surface, it has, I don't know, it might have some waves, and it's affecting the whole signal. It may have some haze derived from the movement of the water. It might have some foam, and that affect basically this part. So with the atmospheric correction, what I was saying, like what we try to obtain is at least the at-surface reflectance spectra, those spectral signatures from the surface. And well, as I mentioned, there are various techniques. Like one of the most common ones is the 6S. But it's not the most straightforward one, because you need the information about the date of when the image was collected, and you need information about how the atmosphere was at that very same moment. Then you have center core, that is the official module to translate to correct the level 1 to turn it into level 2 Sentinel. Then there's iCore developed by Vito. There's the Acolyte, Flash. I mean, there are many different ones. But remember, not all models are suitable for all targets. Like in the case, for example, if we're targeting vegetation, we can use almost all of them. The Acolyte one is not the most, I mean, it's not specific for vegetation, but for the rest, we can use them. But if we're targeting water or water bodies, the 6S, it performs well. Sentinel, nothing at all. Like, for example, the Sentinel-2 data, Sentinel-2 level 2 data is not good for the water targets. iCore is a combination. It has to be tuned, but it's a combination between. It's a good compromise between vegetation and water. And then the Acolyte, it works wonder in water. So, but anyway, this is important, and I was skipping it. Like, their performance is a source of uncertainty, and that's why we need the In Situ data, and to make sure that we are tracking down all the sources of uncertainty to try to reduce them as much as possible. So this is an example of what an image looks like, the top of the atmosphere. And once we correct it, so it's quite obvious. Like the difference is just, it's an obvious thing. We can say, why the sky is blue? Well, we have it in here. This is an example. But then we have this, and what happens when the clouds appear? Because it's not only the atmosphere that we face, but also the clouds. We have to mask fast and furious in a very rigorous way. And there are different approaches as well. I mean, nothing is perfect right now, but there are different approaches for deleting or masking out the clouds and the shadows derived from the clouds, and that's something. I mean, one of the easiest one is to be the most conservative one. As for example, if you use this, you see that that is it gets. I mean, we lose quite a lot of information, but the information that we get is noise. So it's better to mask out or to be very I don't know how to say it, like to be very generous on the masking. It's better to be very generous on the masking that rather than having data that can be contaminated either by the clouds, by the difference. Actually, the difference in the performance is based on the type of clouds, the altitude, the relief, the sun angle. I mean, there are many things, and this is something that you have to get your hands on the data and experience which are the ones that are more well, that they work better for this area, this particular area. But yeah, so basically the roadmap for the basic image processing, just we get the imagery and we perform the atmospheric and topographic corrections. I haven't talked about the topographic corrections because in this area the relief is relatively smooth, so it's not an issue. But in mountainous, in steep, in landscapes with a lot of mountains and a very steep relief, this is something that it has to be corrected and bear in mind as well, the atmosphere, the topographic correction as well as the atmosphere. Then once that we do that, we have the at surface reflectance, and then we perform resampling. Why the resampling? Because, well, Sentinel-2 data comes at different spectral spatial resolutions. I mean, in here I'm only showing the difference between the 10 and the 20, but there are also bands with 60-meter pixel size. So the best idea is to go down to the 10-meter and put in all the bands in the same resolution, spatial resolution. Then you perform the cloud mask, the land mask, or the water mask, or whatever. I mean, you mask everything that is not your target. Like, for example, if you're for the habitat mapping, best thing is just to mask out everything that is not land. And for that, we can use either the masks that are incorporated in the Sentinel-2, but also you can use a combination of spectral indexes or different approaches in order to, mask to exactly identify what are the targets that you're aiming for monitoring. And then once that we have all this, we have the time series. The time series as I was saying, I mean, they are really key. Because of that spectral behavior that it varies along the year. So the spectral phonology. We can complicate things a bit more, and we can use, for example, adding to that bunch of data that we have, we can use in situ data. Like it can be collected, well, the spectral signatures, or we can have, I have added in here just the optical variables, but you can have all sorts of the link with the in situ variables that you're collecting in the field in order to be able to identify the things and the images and to get the information that you want. And something that is really interesting is to use as well the abiotic variables in order to, well, like climate data, data or whatever, in order to allow us to make the classification better. And this is something that Jose did in a project that we had, European project, and it's just an example of land cover mapping and change detection. So this is what we can do with that very refined process of selecting the data and so on. And that's the change matrix. So processing fluxes, I think is clear, but how do we access to the data? Well, there are many ways. Like if we want we can go through the Copernicus services. We have, for example, the Copernicus Land Monitoring Service. There's also, well, they have a bunch of variables. We can select different variables, and then it's just a matter of downloading them. But prior to that, we have to register all of the data that is even if all the data is free, you have to register. That's the main thing. That is something very easy. Another way to obtain the data, in this case is satellite data, is the CREO-DIAS. As well, with a simple register, you go to Data Explorer, choose the choose your polygon or your area of interest and the data that you want. For example, like in this case, we said, well, I don't want a lot of cloud coverage, so less than 5% of the cloud coverage, and then we'll go for Sentinel-2 data. In this case, it was just level 2. Then we have the Copernicus browser. This is the newest thing that they have released, and it's exactly the same. I mean, it's just a matter of logging in, selecting the data, and so it's a straightforward way to obtain the data. And then the interesting thing is that in here you can have as well not only the Sentinel data, but also the contributing missions, which are really cool. In terms of the data analysis tools, I mean, this is something that I don't really use, but it is good for visualization of the data, which is SNAP, and is the official software from ESA. Then you can use QGIS or graphs, like for visualizing the data and do some processing as well. This is my favorite one because I don't visualize the data. Where I go directly. For me, nature are just numbers. I deal with the matrices. I use RStudio R. That's I mean, there are loads of libraries that they can be used, and it's very straightforward. And of course, there's the Google Earth Engine that my colleagues and friends, Gonzalo and Jose, are going to talk about a bit later. So in terms of, I mean, this is, I know that you don't have, there was this problem with the data and so on, but I'm just going to go through the exercise. So the first thing would be just to select the area. Well, first it would be to set the count. It's quite straightforward, but it needs like a double authorization and so on. So each time that you log in, it's a bit. So then you draw the area of interest, select the data, and then load, basically. So it's very straightforward. So the good thing of this is that you download the direct, the archives like that. It's very easy. Like you have both, in terms of the level of processing, you have both the level 1 and the level 2. The level 2 is an official product. So both of them are official products. You can transform the level 1 into level 2, but using the atmospheric correction of your home as something that it works for you. And it's not official. Then the other exercise would be like the data visualization and processing. So for that, it would be using Snap, the Snap toolbox. It's very straightforward, very easy to use because it's thought to be user-friendly. Even if some of the more you use it, the more you will see that it's not that user-friendly, but it's fine. You can. And once that you have that, and considering the data that the images that you have, you can go to the data opening and visualization, the atmospheric correction, and then the extraction of the structural indexes. This is sampling. This is what we get. This is an image from the 28th of April last year. And this is an image from here. Like I believe, I might be mistaken, but I think this is Novi Sad, right? So this is a level 2. It works. The good news that I have for you is that it works pretty well. The level 2 for this area works pretty well. Not really for the water, but for the rest is relatively fine. So if you pass by the cursor, you would see how the spectrum changes, and that's the interesting thing. I mean, and if you open the, and I'm showing you this is the one that I have corrected. But if you open both, the interesting thing is to open both the level 1 and the level 2 at the same time. So you will see how these spectrums changes and how important it is, that correction, because you will, in the level 1, you would start seeing like a very weird things like that. Like, what are those spikes? But the good thing is that once that you perform the atmospheric correction, you get rid of them. So yeah, as I was saying, I mean, there are many ways of correcting the data, and with the SNAP, you have included the sun to core, and this one you can download it and include it into a SNAP. So it has a special module to be included into SNAP. This is my favorite, but it's just because I'm a water optics researcher. So because it deals is the best one with the for the water. So this is an example of what the sun to core atmospheric correction. Well, we can find it. Okay, we go to the optical thematic land processing, sun to core processor, and sun to core 2.12. Once that you get that, you will see that there's a bunch of things that you can change at the window that it opens. My suggestion is my suggestion for you would be to play with those parameters, not the ones that are set, like for example, the numbers, like in terms of the, I don't know, like the aerosol optical depth or whatever, like the atmospheric parameters. I won't touch them too much. But in terms of, I don't know, for example, what happens if you're using the aerosol related to summer or winter? Or what happens if I'm using rural aerosols in the approximation that I'm using, that you can, that's the standard way, like as rural aerosols. But you can have it maritime or the Celtic, and I don't know, you have different things. Then for the resampling, it's very straightforward. I mean, there's this model that you go over there and it's right there, and you can have the 10-meter resolution, and it works fine. Because one of the things that these images have is the format. They have a very weird format, and I'm not sure if I'm allowed to say this, but they are pain in the ass. So that's why I like working with R, because you have the models to open them and you just forget about the format and forget about these things. And these are things that you can do if you have just one image, but you have to consider that you're not going to work with just one image. You're going to work with a bunch of images, and that's not feasible. And this is just a simple exercise for you to see what we get. And the spectral indexes, I mean, there are a bunch of them. Like if you go to the thematic land processing, you have all sorts of biophysical indexes, like the leaf area index of the fraction of apparent photosynthetically available radiation that is related to vegetation or soil radiometric indexes or vegetation indexes, or I don't know, you have a bunch of things there to play around and a lot of information to enjoy with these images. So thank you. And if you have any questions, I'm super available.
Thank you, Anna. Yes, one comment that it was planned like this to spend time talking about remote sensing to eliminate that because we found in many places in our world working with managers, even working with some our bosses, this should not be told neither.
No.
Because sometimes when you work with somebody that is not related to this, and it's very easy to say this is a picture. Again, I know there is some remote sensing people here, and of course this is not new for you, but who to somebody that never worked with remote sensing, it's very easy to say, come on, this is a picture. I download and I put in my GIS and I make analysis. So we wanted to demonstrate, to spend time going through the many issues that remote sensing has behind. So, and we didn't do the exercise for download the snap and correct because we want to, after showing all this amount of things, we are going to move to Google Earth Engine to see how easy, we will see now, how easy it is to do it operationally with Google Earth Engine and these kind of tools that we can just run by using code. That was the idea. And now, instead of blah, blah, now we're going to put Gonzalo behind the black, with the black screen, and all of you also. So the object is quite easy. Gonzalo has many code and exercises that can, if some of you use Google Earth Engine, will be extremely easy. Mm-hmm. But this never works in the first time. You have to do things, you will run the code, and if you want to share your screen.
Yes, just one second.
The reason why we're talking first put this whole video long talk was about just to, was general remote sensing and how you play with a bunch of images, but not many. But if you're using for a really big area, because you can do that, like the download and the processing and so on, for a relatively, not a small area, but it's not, if you don't want to die in the process, it's better not to deal with many scenes. But what they are going to to talk about is, okay, let's go for the big thing, the big picture. So the whole survey, for example, and for the whole survey, all of the time series, all of the available time series, and so on, and that would not be, it's not that it's not feasible. I have done it for the Spanish Peninsula, but at the end of the project, I wanted to kill myself. So the amount of, the amount of data that I had, the terabytes and terabytes and terabytes multiplied by n, because every time that you perform
software,
the processing,
maybe to change the application.
You're producing more and more data. It's just manageable. So they're going to introduce you to the lovely world of school
It's great. No, yeah, but vas a cambiarlo a Google.
Yeah, we can try it.
Yeah. Y si tú ahora mismo pones esto, talla completa, verás.
Okay. Yeah, yes, now, couple of slides that Gonzalo is going to show you, that we are going to show you to put Google on the screen on your eyes. But then the issue is that you log in, start to work and apply and run the code, and do that everything that Anna, more or less everything, I mean, well, some of the options that we can apply to correct the image and to mosaic amount of image for a single moment and to create a time series of one indicator, one index, the NDVI, will be the idea is that you run code and get that information and then explore together what are you obtaining from there. But if we start running the code, we will be in that dark side of the skeptics of remote sensing, let's say, that everything is easy. Will be not easy, but will be, once it works, it's extremely easy. Just click after somebody gives you the code, click and you get the information. But you have to know what do we have behind, level 1, level 2, satellites of different spatial temporal spectral resolutions, corrections, atmospheric correction, topographic correction, where such amount of things that can be in a code written and executed. But we have to know what do we have behind, because afterwards we put together with that in situ information that can have problems or not, then we would like to have everything refined.
So
yeah, sure, of course.
I mean, it's important to really get familiarized with the data, and I mean, and this is what makes the difference between, I mean, for you to discern between good data and bad data, and for make sure that all the processes and steps that you're applying are okay. I mean, you're retrieving something that is reliable and is good and is robust. So this is a perfect way to get familiarized with the data and the targets. And
in my university, we made like in a GIS and remote sensing course that I was teaching like for 10 years. We spent time, it was a way of spending time doing something like a hackathon of bad practices. So we didn't, we just giving step by step the first raw data of imagery to allow the students to do something. Then we correct, then we mosaic, then we create time series. And they were understanding how each step we we were applying to the processing of the image, the information was better and better and more useful. But we didn't do it here. Anna told us many things, and now Google Earth Engine. Do you want to explain briefly what is Google Earth Engine? And well, yeah. So well, basically, Gonzalo wants to be behind the black screen to start work, but basically not spending time now with blah blah. So Google Earth Engine. Somebody works here with Google Earth Engine. I've ever worked with Google Earth Engine. Yeah, the remote sensing people, sure. So of course, you can talk, you can explain, you can punctualize whatever, please. Maybe you are much more expert than us in Google Earth Engine. We have been like, I don't know, 1 year and a half, more or less starting to work with this because we come from another university, the one from Anna. We were working together for almost 10 years. And well, just explaining briefly previously, in the work that we did was more based on pilot demonstrative case studies. It was not necessary. I am simplifying quite a lot, but we had not a need of running very large scales, as Anna told, about the whole Europe, one country. We were working in pilot case studies on which it was enough for running the R code for managing the imagery, downloading the images from in my case to download and to touch and to go to the field and to check the numbers and in situ information. But then we have we moved to the University of Oviedo. We have different projects. One is we are developing one Copernicus Land Monitoring System product. Of course, we are working with all of you here in Serbia. And of course, the timing. Google Earth Engine 5 years ago was starting. You can touch something. Now it's amazing, the amount of information. Not only Google Earth Engine, but any other, Microsoft and other platforms has also something similar to this. Of course, OpenAI that Vito will show us in the next month. And we want also to learn how advanced in that cloud computing capabilities. But basically, Google Earth Engine is efficient for managing remote sensing. Everything that Anna explained, you can, now we are applying, I don't know if you have ever used the topographic correction within Google Earth Engine that you work with. Did you use Google Earth Engine for topographic correction? It's not an issue here in Vojvodina. You are more or less flatter areas. But we in the north of Spain and in alpine areas we're working also, it's amazing the problem of topography for the remote sensing users, because the aspects are very, very, very different in terms of reflectance. So we have to include the topographic correction in our routines. But there is not well performing algorithm running topographic correction in Google Earth Engine. So we are creating or adapting our own routines for topographic correction. So almost everything is done, but the community is quite active, and we can do quite a lot of things in Google Earth Engine. It's powerful, it's efficient, this more or less user-friendly API. You can work in Python, you can work in different languages. The native language is Java, JavaScript, but you have API to communicate with all different languages. And it's time, the most important thing is like 20 years ago, telling, no, I don't want to use R in ecology or science. I mean, we have to use R. So I don't want to use Google Earth Engine or similar platforms or the data information and accessible service, the DIAS of Copernicus. I don't want to use it. I am going to download. You have to get into these kind of facilities with a very simplified way of explaining it. So not only, as Anna explained, different satellites, different platforms, everything is included, different collections with some limitations. Maybe you want to use something that is not included here. You are limited by the information that Google Earth has in the engine. Otherwise, you cannot use your own drones or whatever because they are not annotated here. Well, we want to change. And it's user-friendly because it's that. This is the screen that you get when you start working in Google Earth Engine. Do you want to explain this a little bit?
No, I think it's better seeing it when we use the code.
Yeah, okay. Well, so afterwards you will see the screen and we will explain which is each one of the windows that you have there. The idea is not to go into all the details that I explained because we have no time. And to learn working Google, we put here in the documentation one book that is one of the most accessible ones that when you look in Google. But come on, it's amount of. I learned to run Google Earth Engine, but afterwards Gonzalo came to our labs again, and it's not possible to do everything. And now in the institute, we did it, but now in the University of Oviedo, in the vegetation and biodiversity lab that we are creating like our own multidisciplinary universe of work. So we have botanists, Borja Jiménez Alfaro, and team, many different, like 8 different botanists working in different vegetation types and domains. Then we are a number of postdocs and we are ecologists, I am landscape ecologists with connections with the botany and with connections with the remote sensing and spatial modeling. But the profiles of Gonzalo arrived to the team to just manage data and we think ideas as you have in institutes as Biosense and in IS Cantabria it's the same. You are big institute with a multidisciplinary approach. So the ecologists think ideas and the remote sensing and IT people write code to operationalize that ideas. So Google Earth Engine is more or less that. Everything that Anna explained can be transferred more or less into Google Earth Engine. But what we want to show you now today is what happens if we need for a large area. We would like to do this we will do this together with the colleagues of Vito. Our idea is going behind everything that is done in habitat mapping and so on in Sonata, in OpenAO and so on. But we would like to be like trying things as we discussed yesterday with the field team and so on. Touching the information in the desktop, open the GIS and touching and going to the field and putting the image, but running everything in Google Earth Engine behind. And this example is a very simple example. Using NDVI, we can apply different index about vegetation productivity, about vegetation soil humidity, soil moisture, but we're going to focus in Google and NDVI.
NDVI, yeah.
Yeah, we're going to focus in the widely used and known by everybody NDVI to show you how, for a large area, we wanted to do this for Vojvodina, but we had not the EVA database with us. It is not refined, as we are going to do, as we discussed yesterday with the vegetation field team. But so we are going to show you what we are doing in another biogeographical region with the size, more or less, of Vojvodina, is the whole north of Spain, the Cantabrian Mountains. We were with Vito already in Europa Bon, in the Europa Bon project in that area. Our work with them was exactly the same that the work that we is supposed to do here also in Sonata is prepare everything as good as possible for further modeling. And the models, the habitat mapping here in Sonata will be run using OpenAO with the Vito team, maybe the strongest and biggest company of remote sensing in Europe. We are delighted to collaborate in this line for doing our best, not just for modeling, but to data refining, which from our view is the same. Is you have to prepare everything, but running models also, but not running models to have the final products, but running models to assure that the ingredients of the models will be perfect. And then we run the models. And we want to show you only that how in our study area, imagine that is Vojvodina, but we have not the data refined, the in situ data already prepared to run analysis at the whole country or Vojvodina scale. And we use the north of Spain. So with all the things that I told, we're going to show you how with, I don't know how many lines of code, maybe 100?
Yeah, maybe.
Around 100 lines of code is more affordable. And you can access because we're going to give you, you can look for that kind of code also in the community, in the Google Engine community and so on. How creating an NDVI for that region by using the code, how mosaicing all the images for the large, how many images do you know, more or less?
1 year.
But the number of tiles is like, well, I don't know, 20, 30,
53?
53 different images. Imagine going to a Snap and download one. That's impossible. You can operationalize using Copernicus also, the CREODS or any other platform, they're running code and accessing directly and apply batch analysis. But here it's extremely, I mean, I don't want to say it's extremely easy. You have a learning curve here of certain time, but it's affordable. Otherwise, it is not. So 53 tiles, mosaic, put together, make possible that the mosaic is coherent. So the data are comparable from one tile and the other, making mosaics. And then that mosaic, imagine for 1 month, you can repeat for the next month, and you can repeat for the next month, and the next month, and the next month. Or you can create mosaics for a season. So you have spring of 1 year, the spring of the next year, the spring of the next year, or spring, summer, and autumn of 1 year, and assess phenology. You can do that now at this moment, every 5 single days, more or less, that you have to be lucky because you have clouds, you have shadows, you have problems in one image. And maybe one image of Sentinel is okay, but the next one is full of clouds. At least in our region, clouds are a very, very important issue. So you have to deal with that by modeling the data of Sentinel, by applying some filters, some time series analysis that create values for the pixels that are no data because of clouds or whatever. But the most efficient issue is to create the mosaics, temporal mosaics. You have, imagine in 1 month, 5 or 6 images, and you do your best to put it together and to create a single image, which is a mosaic of different images. To do that click by click is what we call, we also want to apply the handmade way, because there is no, I mean, there is uncertainty, but we know what we are doing. We put one image, we put another one. We collaborated with a company of very good friends in our region when working in IS Cantabria. They continue working with them. ITD, it's a very good forestry people with a long experience of remote sensing. And they spend every week 5 hours of work of one person in the company to mask manually the clouds of the Sentinel imagery over the region. So every single image they receive, there is one operator, see it on a big screen, masking everything that is not perfect in the image. So that analysis that Anna told the pixel here is good. Not that company spend time manually to mask, because applying automatic mask, as Anna told, is tricky. It's not perfect. You have uncertainties. You still keep some clouds and shadows. Of course, that occurs here. We are going to run Google Earth Engine in a very easy way. Easy way, I mean, very just applying mosaics, applying time series, but we keep garbage within our mosaics and so on. That would never happen if you spend time every single image. But imagine, it's impossible. You cannot do that for 54, 53 images every month. So it's impossible. So we have this. And the idea is to obtain time series of NDVI of that mosaic, see how evolves the NDVI in time, and then to make ecological questions on that time series. Imagine that, as Anna told, that I will show you also afterwards, 1 pixel is forest. What happens with a forest through time? Forest, at least in our latitude, I think also here, we have winter with no broadleaf forest, no leaves. We have winter, so no leaves. NDVI. So all of you know NDVI. Yeah, it's just vegetation productivity, vegetation biomass, a proxy of that. It's a combination of bands that if value is very low, you have no photosynthesis. So you have no vegetation in action there. When the value is high, you have vegetation. Very easy. We can do that for every single index, every single indicator. Talking about physical, we always try to work with the nexus carbon, water, energy, something that has to do with the amount of biomass, carbon, the amount of energy, the physical energy received from the sun, and water, about soil humidity and so on. NDVI, well, again, forest, no vegetation, quite low value. In summer, the canopies, the leaves are growing, and the canopy is full of green biomass, so the value is the maximum, and then it decreases. If you cut that forest, you are not going to have that curve, and you can see here for every single pixel through time. So the best thing is just to start work. So Gonzalo is gonna share the screen in Google. No? Okay, you're watching the screen. Yeah. And the idea is to log in Google Earth Engine. If some of you has already used this, will be very simple, but you go to the web page. So let's go step by step to assure that all of you are there. I think that everybody has a Gmail account. No? Yeah, you can explain about step by step what to do.
You need to
another account. Yeah. Just like Gmail, you have to sing in. And one of my master students I think she was master student 2 years ago. No, 3 years ago. Gonzalo and me, we did also the master. He did master with me, and then we started to work together and with Anna, and now he moved to my new place also. That girl is, ¿cómo te acuerdas? Lorena Caiza Morales was a girl from Panama, or I don't know, or Dominican Republic. Dominican Republic. She did the PhD with me, no idea about Google Earth Engine. So she started to work, and now she's one of the most famous girls in South America and Central America, working with the mangrove forest with Google Earth Engine. She worked with the FAO, with the United Nations, with the Latin American countries running. She has an algorithm with patente, how to say? Patent. I'm going to invent patent. Well, her own algorithm registered to run analysis with Google Earth Engine in the mangrove forest. And she started 4 years ago working on that, but she focused only on that, and it's amazing, this girl now. So to work on with Google Earth Engine is just to spend time working in Google Earth. Okay, so this is the first Sorry for the word stupid step. It's just logging in. That sometimes, I don't know, we have to, and when we go, we had problems with OneDrive, something because of that. Everything was ready, but my OneDrive is not working. I had to put some code several times and it blocked.
You can do it.
No, no te deja.
No, me pide que mando un mensaje de verificación.
Y no te llega.
Yo espero
No
con
tengo
el,
cobertura.
y con el,
Da igual, llevas, sí,
con el autentificador.
En el Safari siempre llevas. So, again, this was not expected. I don't know. ¿No te llegó? ¿No te llega mensaje? Te va a llegar. Es que me ha pasado a mí. ¿A que no tienes el número de vecinos? No. What? This is problems from unexpected one? I know why. ¿En tu ordenador lo tienes? ¿Y pones tu ordenador?
Y si quieres tu ordenador, te lo...
No te estés pidiendo, haz de más. Ya arriba. Ahí está. Okay. So all of you were able to log in? You are there? Okay. Sorry for,
Do we create a new project or choose an existing?
If you have an existing, that's good. If you want to create a new project, that's good also. Now, Google Learning is changing, quite everybody's using. I don't know if Google in 6 months, 1 year, or whatever, could say, okay, do you want to use it? Pay. Now, for the moment, you have not to pay, but you have cloud storage. This is not affecting the computing capabilities, but it is affecting the information that you want to keep and to storage when after processing, and you have to pay the Google Cloud account and so on. So, it's like in the middle of a risky issue to spend time and money on this, and maybe one day Google is telling, stop, guys, pay. Okay.
So we have two different scripts. The first one we use an unfiltered image only from the Copernicus data level 2 that I explained before. And the other one we apply a different filtering about cloud, snow, and all that we can imagine.
Yeah, the idea, as I started talking, I didn't explain specifically before, is to apply two analysis in Google. There are two separate scripts to make it easier. One script use the time series. The images are corrected. Has no sense to not to correct the images to level 2 because we use the collection that has the image corrected already at level 2, but without filtering
and mosaicing the clouds and
the clouds and
snow and
unfiltered is without applying the shoe already.
Yeah.
Unfiltered is without applying mask for clouds and shadows.
Yeah.
And filtered is applying that mask for clouds and shadows. But all the time series of imagery is corrected. The whole time series is corrected because it's level 2, as Anna explained. For that reason, even though it's quite quick, it's important to have knowledge on remote sensing to now start talking about this is level 2 without filter of cloud mask. If you have not heard before, Anna, they're like, come on, what's level 2? Come on, what's that of cloud mask? Okay?
No, I would just like to zoom.
Okay. So the first thing is to learn how to import the script.
Yeah.
I would say. So if you are logging in, you can just write down the code from scratch that come on with ChatGPT and so on, and the amount of resources has no sense. The important thing is what Anna explained is to know what to look for. I want to do this, look for that, start to touch the codes and see what is going on. And then you create a code in an external editor or whatever and import the code. So explain a little bit maybe the window.
Okay, this is the area of the script, the center area. You can see the map just beyond. and the different part, the inspector or the console to see the consults you make to the script. And here you have your own script, your area of work.
Yeah, when you here is the area in which you have the script that will be executed, and when you import, we have in the presentation there is one slide that explains what is every single part of the Google editing console. Are you some of you have never used this? Never? No? Okay. So maybe if you go step by step to import the code would be easier.
Okay.
How to import, because you have in the folder that Maya sent you, you have the two scripts. So what we're going to do is to import first to import
or create a new script. Maybe.
Yeah, okay, as well.
You can do a new file. Select your work area.
Okay, so let's do it step by step. What Gonzalo has done is to go to your script window and create a new script. Isn't that?
Yeah, a new file, and you can copy and paste the script that you have in a text file.
So do that, or es mejor eso importarlo.
To import, you only need to copy and paste the repository file.
Yeah. Well, let's follow these steps for how it works. So you have the script. You can go to your folder, shared folder. Do you have access to the shared folder? You can go and copy the first script that is called and filter. Okay.
This is session 2, right?
Yeah,
Session 2.
Yeah, sorry. Yeah. Yeah, session 2 and the second folder, the third folder is called hands-on. You should have there the scripts. One is called workshop and filter. No?
Yeah.
You can import also the script, or you can, Gonzalo did, to create new script and we will copy and paste. Doesn't matter.
Can you repeat which script?
Yeah. Yeah,
New and file.
Yeah, Gonzalo is doing that because my computer is crazy and he has not access to the shared folder. But we have one anyway.
¿Dónde está la carpeta?
Sí.
Espera, la voy a...
Estamos en remoto, pues nada.
Yeah.
Yeah, because we are working in remote from my computer because it became crazy. So it's not direct access to the information for importing. But anyway, let's do it like that. It's gonna work as well. Okay. So if you create the new script and you go to the document that you have, to the small code that you have in the session 2 hands-on, open that text file, copy and paste, you will have this one. Yeah.
A ver, espera. Puta mierda, no lo puedo jugar, la verdad. Bueno, pues creo que vamos a seguir así, pero voy a bien.
Well, so let's do it. Sorry for my computer. I don't know what happens. So if you copy and paste, just put in this Gonzalo, the workshop and filter. You should have something like that. It's okay? Okay. Sorry for not. We can import, but now we are showing the information from my remote desk and go. I know, but something happened with OneDrive. So if you have this, that's the script for running the analysis with the unfiltered time series mosaic of Sentinel-2 imagery. And now, if you want Gonzalo explain each block, what does it mean? Because the code is run only once. It's not like in RStudio, you can select and run partially. We're going to run the whole code, but just to understand a little bit what happens each block at each block.
Okay, the first of all, you need to import the save files. You can do it clicking Assets, New, and Save File. And you select in the folder, you can find a zip called Vegetation WGS.
Yeah.
Yeah. If you can do it, or I play with my script.
Yeah, it's just like a typical GIS to look for. I think the best thing would be to download the shared folder to your local hard drive and to put in a small root, for example, D or C Google Earth Engine, something very, very short to look for the content. If somebody's not able, just let us know and we can move.
Yeah, just wait for.
Yeah, sure. Wait, sure. The end is like learning to use our GIS, QGIS, and then the code is another thing. But now the AI arrived to our lives, so everything's easier.
Already?
No, don't worry. Somebody needs more time.
Hay que cargarlo de acá. Tiene que cambiar.
Bueno, para que no vaya.
Para que las funciones.
Sí, eso dice los errores. But even though the code is there, of course, it's like in a code of R. We have some roots for the data that need to be updated to your data. Otherwise, it's not going to recognize Gonzalo Hernández Romero is not your account. So once you upload the shapefile, you have to change that.
Yeah, you can find the root.
So everybody uploaded the shapefile?
No, I'm talking about, for example, I'm.
Yeah, you can repeat, Gonzalo, to upload the shapefile.
In Assets, New, and Stakeholders. And subject file, and you select in your computer.
Yeah, for that reason, it's much better to download from.
Don't zip.
Yeah, don't unzip.
Select the zip. The zip.
The compressed file, not too uncompressed.
It's not necessary to decompress.
As in, if you start to work in GIS, it's not efficient if somebody open a GIS and go through all the options that you have in one GIS. So it's much better go step by step, learning what you're going to use. Otherwise, so for that reason, remember for now, to recap, what we have done is to create a new script. We can import. That's straight, but Gonzalo cannot access to because of my computer. So you can create a new script and paste the code. It's the same than import the script, looking for it, and import the script. Exactly the same. Then we go to assets. It's like inputs that Google Earth Engine needs to run analysis. And the input, the specific one, is the shapefile of points. That points will be the final step. Well, CSV, whatever. I mean, the shapefile points. That points that you are using are the last step that we have to create here. That points were collected in the field by the botanist, were refined by using our routine in Google Earth Engine, that we are creating an entire routine in Google Earth Engine, following 3 steps that I will let you know afterwards, to refine the data. So once you finish your work, that will be raw data of field work that will be coupled to remote sensing. So that points are the final step, are good. So no uncertainty and so on. So did you import the shapefile?
Yes.
Sorry? Okay, perfect.
It says the file.
The CSV. No,
Have a correct extension.
To the new.
Yeah.
What? Come on.
Was I supposed to collect all of them?
Well, you have to import the compressed file.
Oh, this.
Yes, sorry. Yeah, you have to import the compressed file. The Google Engine reads not the shape file, the different files, but because having only one archive, you need to import the set IP compressed file to have all together, and then the machine uncompress within. That's a clever decision for avoiding selecting all the components for a shape file.
Just scroll down at the end of the script, you know, just see what you have.
Yeah, sure.
Oh, vegetation types. Vegetable.
Until where?
Yes. At the end. It requires SHP. Okay. I think.
But it requires SHP format. It's not the rest folder is not.
It's also in state.
That one.
Yeah, that's the one. You can progress
Upload?
Yeah.
It is not. If you are going against the folder shared by Maya, or you download it? No, download please. Yeah. Maybe because the system has not access to the shared folder of the Sonata project, you know?
But I uploaded it.
You download it? It's in yours. Okay. But it's in OneDrive.
Visualize the map.
Ecco, un agosto 3
Okay. Yeah, copy just the shapefile, copy the station types, copy. Yeah. Yeah, this one is uncompressed. And go to directly to C, directly to the system, my own
I just realized why you asked.
Yeah. Even though this became complex, this is reality. If everything was like perfect, it could not have been real. I mean, yeah, you spend like a couple of months working with Google Engine until, oh, come on, it was doing this and this and this. It's like R, but with more technology behind, let's say. You go to my computer. We can anyway, yeah, this my PC. Okay, open C, put it there. Put it there. And let's try once you. Yeah, we want to go. Yeah, you have to, if we or some of us can upload the shapefile, we can stop recording. And then we continue with this.
Okay.
¿No lo tienes? And try again, just to try, because it should have, I mean, it's not said. Yeah.
Yes, and that's the length of the view.
Okay.
It's like folder with you, right?
Instagram, sì. Questa è la lingua corretta.
Number 2 there, yes, behind that. Okay, open number 2 after, yeah, because that's number 2.
Maybe finally. Ayuda. So I'm quite sure that I missed some of the steps. I'm not sure here.
That's yeah.
So the path.
Yeah. She had problems to upload the file because of the path was so long. So you can have, well, this is one of the basic rules of every single GIS. So the paths need to be short, extremely short, with no strange characters, and in your local hard drive. So Google is not accepting at all that you put into your OneDrive, into a shared folder or whatever.
Google and Microsoft.
Yeah, Google and Microsoft. Now it works because he put into C the hard drive and just the file, and it's uploaded. So well, at least the code, we can assure the code work. So we can stop for a coffee, and we come back because once you put the shape file, then it's just a matter of executing the code. Just that. It's important just to understand a little bit what the code is doing. And what the code is doing is what Anna explained before. But written in a code for making it operationally at every single point in the world. If you change the shape file to the points of Bolvodina in the field, it's going to work as well. Exactly the same. That's the magic of the code in Google Engine and
Can you change the order and put the point on top of the image?
Yeah, sure, of course.
The points are in Spain somewhere.
Yeah, the point should be in the Calzada.
Like this or
Yeah, they are yeah. We can, do you want to stop for a coffee and we check that everything is working properly and we come back in 10 minutes?
Yeah, we can have a few minutes. I think it's the time for this.
Yeah, it is the time.
Yes.
No.
Yes. But Sarah, are we supposed to see one file in assets or all of these?
You have to see the file here in assets.
Vegetation.
But only one or all of those?
Yes, vegetation types. Yeah. Sorry, because Gonzalo here has many things.
Yeah, it's only
You have to
vegetation
see only
types.
vegetation types.
And copy this link.
Yeah, nos vamos a tomar café.
Okay.
Well, so we just this and we move to the coffee.
Okay.
Once you see vegetation types here, don't worry about watching in the GIS
Okay.
screen, but just go to the file.
Click and copy the table ID.
Okay.
Okay, this is my table ID. You have a different one,
Just that in Google.
and you come back to the script and change this root and put the new root.
Did you see that? It's just, do you have the file here? Well, go to the file again, please, in assets. So you go to assets. This is your user of Google Earth Engine, and you have to have vegetation types, WGS. Okay. You click on it and have to copy the table ID. Just that.
Just type table ID.
Yeah. Because what we are doing, imagine, I think that all of you work in a GIS, in a normal GIS.
Yeah.
No? If you imagine that you open a project of ArcGIS or QGIS, and you have a project on which you have Serbia, and you have points on Bolvodina, only that, and you have a base map of Bing Maps or whatever, of Google Engine or whatever, or Google Earth or whatever, and you have the project and you store the project and close your computer, and then you send the project to another person, and that person open the project, and you cannot see anything on the screen because the system doesn't know where is your point save file because it's in your place. So what you have to do is to click on that different option, that the different software, and go to look for the file and say before it was in d.gis Tiana and now it's d.gis Maya. So you identify the file and the system works, and you can see the points. This is just the send. Instead of the user Hernández Romero or Gonzalo Hernández Romero, it's your user, so you have to give the path to the system. Just that.
So I copy this and go here.
You copy that and go to the, when you copy, you go to the script,
Your own script.
your own script.
Oh, yeah, I did it,
And-
then change.
And you change the red,
The red.
keeping the semicolons, okay? This is not the normal way to learn Google at the gym.
I have a question.
Yeah.
Why, I'm really curious. So we have ArcMap, then we switch to QGIS and those guys like or R. What is the advantage of using Google Earth Engine?
You will see in 30 seconds after the copy. So now it's done. Gonzalo, correctly, please, if I'm wrong. Without changing this path, you can apply the code in any part of the world. So if one colleague of you from Mexico is giving you points of visitation of Mexico, you can just put there the same file and the code runs automatically in any single part of the world. If you work in R and in QGIS and you download the image for Bolgodina and you create the mosaic, correct the images, clouds, and so on, from this year, no, from 2024, and you want to update until this year, you have to go again to the solutions that Anna showed, download the imagery or do it in R, but you cannot do, using R, you cannot download the whole survey in a while, in 30 seconds. You cannot, because the program will explode. It's impossible to process that information because you cannot do in the cloud. Because Google Earth Engine, you are not downloading anything. Google Earth Engine is already a big building like this in the middle of the polar Arctic with the servers of Google that they are storing, not only Google, Amazon, Microsoft, and so on which they have all the Sentinels available, all the Landsat available, Modis and Pleiad and so on.
This image was not uploaded by us, it is in the cloud. And we just give the.
Absolutely. This image is not in well, the image is your image because you process what is not.
I put a run, yeah.
Yeah.
Yeah, I press the run,
Yeah.
okay.
So what is in the cloud are the Sentinels.
Okay, so you just provide this shapefile and then you run the code and
Yes.
above.
And then, as Gonzalo will show, you can download the image that you create. You can download the graphics, the time series. You can combine with other information, but everything is done in the cloud, and you only download the result. And the cloud it has 53 images. Imagine 53 images every single month, but one single month is not 53 images. It's a mosaic of 53 images.
I understand.
Times four.
The shapefile is the extent of the area he is using for calculation.
No,
Yeah.
the points.
Yeah, the
The
points are
vegetation, the vegetation points.
Okay, but the points, how he can choose, okay. So those are the points, but he choose this square because that's the extent of the points, yeah? Deep right in the script, okay.
What we can do afterwards.
I didn't.
Sí, el cuadrado está anotado el extent. Está anotado el extent. Well, so what? Yeah. Of course, if you don't annotate the extent. So Tiana, if you don't annotate the extent, the system, I think, the system gets the boundary of a shapefile that are giving you a context. That below in the code is annotated the extent, is one tile, no? One tile of something.
No, it's smaller. It's a
it's
polygon
within one tile.
only cover the points.
Okay, so we can just go straight for a coffee and spend 10 more minutes to understand quickly the code. Yes, you can go through the code. This part do this part does this other part does this. You can run the code.
It's all commented. We can
just go quickly through the code and you can see the result. Okay. This code, as I told, can work in any part of the world on which you have information. That's the benefit.
But if you don't know how to write the script, you need help from them, and then you just use that script and click run.
That's a very easy way to see that, but yes.
Just like
Yeah, but even though you know how to create a script, I I dream never touch Google Engine again with Gonzalo nearby working together because you cannot, I mean, if you want to be an expert in wherever, Google Engine, in R, modeling or wherever, you have to focus on that.
Yeah.
The good thing is to communicate and say, I would like to, now what we are creating in Google Engine is really amazing. Working with technically Gonzalo, with another girl from the South, that is a postdoc that spent the whole PhD in doing this, with some, of course, ecological question, hypothesis, but the powerful of that girl is to work, she thinks in Java, so she transferred that thoughts into the Google Engine. And we give them the ecological context for doing whatever. And what we're doing is everything in Google Engine, since once the data collected is already here, everything until having the final habitat map is just programming Google Engine. So let's go to our copy, I think.
So thank you for that. And now I get. But we can teach them the data.
No, pero lo que nosotros me pegado igual. Pero mola porque es como, ya es complejo, pum, pum. Y luego, aquí, el problema del login y tal, pero es que hasta queda bien. Es que el login lo vas a comer. Sí, de alguna manera.
Es increíble que lo más difícil sea loguearse.
Entonces, luego lo suyo es ejecutar, ver el resultado. Y
Yeah,
Yeah.
talk to him.
Hello. Hello to the people in the matrix. Can you hear us, Jetse?
Sorry?
Okay, nice. How are you? So, Jetse, we are with a little bit of, well, I will introduce you afterwards. People is around here. We are a little bit late with the agenda, with this Google Engine things, when logging in and so on. So, if you want, we can stop. We can end up with the explanation of Google Engine, and for not touching your agenda, if you have to move, we can talk first about to make first your presentation, and then I will do mine afterwards, just for giving you freedom to stay or to move. Okay?
Yeah, because I have another meeting at
Here.
1, so I have to move at 1. Yeah.
That's perfect. So we will use like 10 minutes to end up with 15 minutes to explain, to go through the script and to see the results. That's what we can do, at least for closing this chapter of how making operational this amount of analysis that we can do with remote sensing. And afterwards, it's time to move to the second half of the workshop about soil modeling or vegetation modeling. Doesn't matter.
Yeah.
So you can talk first,
Yeah.
and then if you have to leave, that's good. So,
Okay, perfect.
a slide change in the agenda. Okay, we will talk
Excellent.
first about digital soil mapping, or just not to move the agenda from Jetse, who is quite busy, and thank you very much, Jetse, for being here. And then I will talk my stuff that is more open to discussion. You will open the GIS, and we will recap what we explained yesterday about the soil, the in situ information as well. So, well, again, let's continue with the Google Earth Engine. This nightmare, that is a beautiful thing, that is a nightmare of a beautiful nightmare, a nightmare of beautiful or whatever. So the only thing you have to touch, as we told, is the access, the path to the vegetation type. Tiana wanted to see on the top. So, but it's good that comment, because please don't think on Google Engine as a GIS. This is a dark window. Now it's white. We can put it black to get results. So if you want to see the points or whatever, go to the GIS. It's much better. Not to touch or not to try to move or go, oh, this option I like, because maybe everything start to crash. You can do everything, but this is not the correct, polite way to learn how to use Google Earth Engine. But there is lots of documentation out there. What we wanted to show you is that this code takes everything more or less that Anna explained.
No, not everything. Eh?
So, but the guys told me that, like, if you want to change it, then you need to change the script, basically.
Yeah, sure.
Okay.
Maybe the script can be even more operational, more cool, organized. But anyway, the idea was to show you that it works when you click the code. Of course, you can do more things, you can organize it better, whatever, but it's just a way of transferring that explanation of Anna into code. But as I told, of course, also that comment is good. Don't try to see this like a GIS that you can use. For example, there is a beautiful layer now, it's canopy height of Meta. It's a layer for the entire world of vegetation height, vegetation structure at 1 meter of spatial resolution, done by Meta, the owners of Facebook and all that things. And you can access with 2 lines in Google Engine and explore and check and whatever. Of course, it's a GIS in some way, but the main task is creating data. For example, all the mosaics of Sentinel to run our models afterwards in R and so on, we created in Google Engine. So we use it for downloading the Sentinels, not for running analysis. I have one friend that we have been talking with Tiana now, that they are creating code in Google Engine for running Biomod 2, it's a species distribution modeling algorithm within Google Engine to make the use of the collections of time series of satellite directly in Google Engine. So there is a vast amount of work done on this, and really people working specifically on that. Because of that, Gonzalo fortunately joined our team for start to spend the time specifically on this. Okay? So the code, even though the code can be rewritten and optimized and so on, the code does everything that we need for having two things. One map of NDVI that we can repeat monthly or wherever, and time series, the graph with the time series. No?
And obtain the NDVI values to the point, to its point.
Yeah,
In a
we
specific
create
ARC.
the image, the NDVI, as a result of the Sentinel imagery. We have one NDVI, and the next month, and the next month, and the next month. And because we have the points, we obtain the points from the NDVI, so we can see the evolution of the value of the NDVI of the points. What are the points? That's what we are going to explain afterwards. The points are in situ data collected by our botanists in the north of Spain during the last 5 to 6 years. They went to the field, they collected information from forest, shrubland, grassland, habitat types, different habitat types, following the UNIS classification system and transferred to the Annex 1 of the directive. So the points are good. And now we create the time series of NDVI for getting information on the values of NDVI for that point. What can we do with that is what we are going to check afterwards in my presentation. Now the issue is to get the values of the NDVI to the points.
We can play.
Yeah, if you go through the code,
Okay.
just to explain briefly what we are doing at each step of the code, that would be nice.
First of all, we import the save files. We done. This function center the map in this below, and you add the same poles. To see the vegetation folder, we use this new function, and now import the Sentinel data. We are going to use the surface reflectance corrected official from Copernicus. This collection, but we in this script we are not going to do anything more. No filter clouds or mosaicing. The next one, we calculate the NDVI and NDMI for the collection. First, we create a function using the bands. You might want to look in the PC.
Oh,
a battery.
Yes, no, I will show.
Okay.
Continue.
NDVI, NDMI, and we apply the function for the collection, the Sentinel-2 collection.
You have to fill them.
The next, we are going to extract the values for each point and import the result to a TCV. This TCV you can join in the hits with the original points, with the ID or other code. Next, we are going to visualize the results using a mensual graphs for all the. We first obtain the monthly mean of each index. This is one filter. We obtain the monthly mean of each index, and we print in a graph that we can see in the console now. And we select 2 or 3 vegetation types so to see more clearly. And finally, we create the NDVI image. It's only for NDVI. For NDMI, it's the same, only change this one.
Okay, thank you. So the idea of this was going through an explanation is if we think on GIS and desktop GIS, QGIS, RGIS, and we think on we know already what is a satellite image, where we can access. So the good thing of this, in fact, I will start my explanation with a couple of pictures that looks through the window and imagine what you would like to do there, but transfer to technology. So we have points. What are the points? Try to see guys like these 2 botanists going to the field and collecting, okay, Quercus pyrenaica in this coordinate. I know which is the species, the accompanying species, whatever. So 1 point. Then I move grassland of whatever type and so on. And then what Gonzalo told the unfilter is that let's try to see which kind of NDVI values I have through time, through the year 2023.
Yeah,
but we can repeat.
You can change.
Since middle 80s with Landsat and since 2017 with Sentinel. Let's see which are the values of that Quercus pyrenaica forest through the months of 2023 in this case, but we can do through the years using the whole time series of sentinels. And even we are creating this script, these routines much larger than this with Landsat, Modis, and Sentinel all together. So we can do whatever. And you can ask why I have to believe that these guys collected Quercus pyrenaica. And then appeared your experts and psychologists. I know what happens with Quercus pyrenaica. It began to have leaves in a specific month. Then I have the crown canopy full of leaves in August. And then it begins to lose the leaves, but the leaves are not going to the floor. The leaves maintain. Quercus pyrenaica is Quercus pedunculata, or is the marker stem the one that is not putting the leaves on the ground, that keeps the leaves? Do you have not that?
We don't have.
Okay, sorry.
those.
I thought, yeah, it was in Turkey. You know, they say an oak forest that when the leaves become senescent, they are not going to the ground. They maintain to protect the new leaves in the next season because of the frozen, because of the low temperature. So, and that became very different in the eyes of the satellite, that oak forest from other oak forests. Yeah, well, we will go into the spectrophenology afterward. But yes, the thing is that the satellite imagery is correct, but it's not mosaic for the clouds, no?
Yeah.
Okay. So everything is okay. The points are good. We know that these guys made a very good job, went to the field, collect information, that's good. Then we put the imagery there, it's corrected atmospherically, and I made the mosaics time series, but we forgot to mask the clouds. And we are going to have an NDVI map, and we're going to have a graph with the evolution of the values of the NDVI or NDMI or whatever, but in this case, NDVI for that points collected. And if we run the code, it's done.
Only a little select of the points near to below,
But it's with the same
and you can see the results in the
filter. I
the
did
console.
When I make a new file, what I do, new file.
Yeah, you have to new file.
Okay.
Yes.
And then put
Yeah, put the name.
Yes.
Like the new name.
Yeah.
So
Just
Well,
that now. Yes.
yeah, that's right.
Full display.
Yeah. So the difference from QGIS, R or whatever. So please, the remote sensing people, correct us, specify whatever. Of course, we are here to discuss, not to. Maybe we are wrong in some whatever. But the main philosophy of the idea is just this. So without anything else that creating the code, so like come on, anything else, explain Gonzalo, anything else, or the remote sensing people that this is not straight. But this is the evolution. These are points. We have now, how many points do we have in the Europe of Spain? I think it's like, we have 5,000 points of UNIS habitat types at the level 4 in our region, 5,000, 8,000 points, and I don't know. Each point is validated in the field and so on. This is just a number of points, a few points of different alpine grasslands, shrublands, Quercus pyrenaica, Quercus uber, Quercus rotundifolia, some wetlands and so on. And that's the evolution of the NDVI without filtering. No?
No filter. Only for ours, and we can see to only this one, maybe more clearly.
This is just the evolution of a beech forest, Quercus pyrenaica forest, shrubland, and grassland. So, well, we can go into details or not, but the idea is to see more or less, in general terms, we are talking about shrubland, grassland, and forest. And the good news is that in the winter and early spring, NDVI values are smaller than in summer, and in autumn are smaller than in summer also. That's like the general pattern that is good, but there is some random term.
No, it's discovered. No, the pattern discovered, yeah. But this is the unfiltered.
Yeah, but look here. We have one maximum peak in February. I don't know why. Then there's some random movement here that some values of the beech forest in July has a smaller value than others. Of course, think that the image, as Anna showed us, image has clouds moving around the image, and the points are distributed around the image. So this is context dependent. That one point is not working properly, it does not mean that every single point is not working properly. because you can have good data in one point when you have the shrubland, and bad data at another point on which you have grassland. And of course, this changes month after month. If instead of doing this as a monthly mosaic, we have, instead of 12 points, we can have for one single year in grassland, how many points? 54? 50.
Near the 50, yeah.
We are running a paper now on which we are trying to map alpine grasslands by combining with data loggers in the field for the last 4 years. So we're trying to map the distribution of the different communities by using information from the data loggers, from soil humidity, pressure, temperature, and information from the remote sensing. So what Gonzalo did there was to get the information for every single image without mosaic. So many points, but if you see the evolution of the values without filtering clouds and so on, it's like madness completely. 1 point maximum value, then 0 value. So if you now, it's not sorry to do, but if you open the other script, the one filter and run, let's check the result. It's just only putting the shapefile path in the other script and run.
Yeah, you need to change the path again.
Yeah. Yeah.
About the shape files, is that sort of specific format or this is just regular shape?
It's a shapefile and put in a shape.
For example, I made
So this is like what sort of attributes we can,
I don't know.
Yeah.
like an attribute table.
But if
You can
Because
say.
this is like a points or yes, am I
The
right?
points are the location. Yeah. And the attributes can be whatever you want. Imagine that you have there as attribute, you have the biomass of the parcel that you
Measured, for example.
Yeah.
Measured, all right?
whatever.
Okay.
You go and you calculate the stand of 10 by 10 meters, imagine, you select 10 trees, and you calculate the diameter of the breast height.
This is the filter.
Any format.
And now I want to
You find.
It's just if you have coordinates.
It's not
It's a shape file.
Not points, but
like that.
let's say lines or polygons or.
And then I.
Well, you can do it, but it's slightly different.
Second.
But the easiest way is to just include the points and
No.
give the value from the points. You can use polygons and you can give the average value of the
Yeah,
polygon.
of the
That's how I
polygon.
change
Yeah, but it's because well, it's
You
another.
should have like a weight.
I don't know why
If you
it's-
have, for example, like
the same,
not
it's not
only
the
one
same
measurement
from
in
my
the polygon, like 3 or 5, you should
Yeah,
average
for
and
example.
make a.
But also, when you have 1 point, what I'm going to explain it afterwards is that 1 point can be assessed in terms of quality more easily, but assess the quality of 1 polygon is more tricky
Mhm.
because it's 1 polygon can have a lot of variability within.
I don't know why.
Yeah, like we
copy
did
the-
with the soil sampling, like one polygon.
Yeah.
consists of 4 polygons
should be
and
empty
small-
first and
Yeah.
not
polygon
Now it's
consists
empty.
And
of
now I can
four points
Yeah, now you
change
copy.
and change the name
Uh-huh.
again.
We are in fact creating an algorithm.
Okay, do you know why this happens? No.
Moves from
Sorry?
points
Why
to
this
polygons.
happens? No, you don't know.
versus the
I don't know.
variability. Also in Google and Engine. Yeah. So well, just to end up with this and allow Jetse start with the modeling side of the workshop. If you open the result, and it's generating still.
It's the code is very similar. So this is all the filtering process that we add. These are in different steps.
All that is the filtering.
All that. Yeah.
So now we do filters.
Yeah.
Oh.
And the filter is not just one line. In Google Engine, now we are exploring in our project like 4-5 different filtering algorithms that we have in Google Engine. We are putting all together, plus topographic correction, and we are exploring the results for each one against the no filtering to do some kind of sensitivity analysis to create the final routine we want to use. The bad news is that the best filters that we have in Google Engine are not applicable for all the Sentinel collections. So it's like only you can apply for Sentinels after 2021, something like that.
Yeah.
So if you select the let's say the worst, the older filters, as Anna explained, the ones that are not so accurate, you can apply to the whole time series of sentinel. But the new filters can only be applied in the last sentinels. So it's tricky. There are some trade-offs to take decisions. And all this, remember, is to actually all this, of course, to show you the tools, but is to eliminate that general thought of remote sensing as a picture. So not only taking into account the complexity of learning and understanding every single step, that is very important. I have many discussions with Anna when working together. We continue working together, but nearby, because I want it to be more operational. Come on, we have to map this in Europe in 12 study sites. I don't mind if it's water or not. And the discussion was, yeah, come on, but if it's water, we need to use acolyte from Vito. Silió send to core is not working in the blue haze and so on. So it's a trade-off against the quality, that if you don't apply that quality, your results will be worse and maybe unuseful. And if you don't go quickly, you are not going to finish on time. So it's a trade-off, but at least we have to have in mind all these things. And the way of working is like Sonata and other multidisciplinary projects on which I don't mind after explaining to the botanists how data are collected, because that's their role. And I assume that it will be perfect. If I do that job, I will go quickly and get worse results. And the botanists, once they give you the information, they don't mind whether NDVI have clouds or not. But the points are perfect. If you use that perfect points to check the validity of the NDVI time series, and you discard points or you discard NDVI time series, but you are not creating a very good meal with stones. So we didn't show this before. We have put again, Gonzalo, please, the Google engine.
Oh, sorry.
No, it's okay. Of course, you have all that. Every single point is over a monthly mosaic of Sentinel. You have the image. You have the NDVI already there for every single month, and you can download and go to your QGIS. Imagine doing that with a Snap, downloading, correcting, processing every single image. No, processing 4 or 5 images per month to create a mosaic per month, then to do the next month, the next month, the next month. And imagine to do for the whole Serbia that you have to process one tile, another tile, another tile. Manually is important, it's impossible. You can write batch processing or whatever at any platform, but this Google engine, and of course, Vito will have the meeting in, the workshop in March on OpenAO, is the evolution on all this. It's much better structured, much more operational. So this evolution of technology and needs of the intermediate users that we are thinking always in the needs of the end user stakeholders. So, yeah.
Just a technical thing to finally download the different archives, you need to go to task and run again only to obtain the final product. And this is going to your Google Drive account. And you download from the Google Drive. But you don't download directly, it's by Google.
Yeah, because this is important, or many small things, that everything is done on the cloud. So unless you tell to the system, I want to download this, never is going to be downloaded. So in this case, you have this tool in the task run for downloading whatever you create. But you have to tell specifically to download, otherwise you're not going to download. You have the information there. It's like in R, you have an object, you work with the object, but if you want to export, you have to write down, I want to export this as a TIFF file. So you export. Otherwise, it's in the R workspace to run analysis. Here is in the cloud of Google. Yeah. So the images and the two, the one that, that too. Yeah, this is the evolution. And it's really clear. And it was, maybe you cannot believe us, but it was not addressed for getting good results. These are points for the Cantabrian Mountains, different ecosystem types. And this is unfiltered, and this is filtered. Of course, this is not perfect because this is not a laboratory. This is reality. But you can see that the left image is much more stable, reducing the variance and increasing the
values in the filter that are higher.
Yeah. Oh, yeah. And also the values are higher. That is more real than the 0.1 to a beach forest or a scrubland. So what happened here is that we have less values for assessing the evolution, less values for creating the most sites, but more accuracy in the time series. Okay? And again, it's a threshold. How many values I would like to lose for getting my time series, acknowledging that if the filter of clouds and so on, we have many different filters and topography and so on, eliminate bad information from the time series of imagery, which is the point of saying, okay, this is my perfect threshold. That's a dream still, it's not resolved. It's an arbitrary decision of the expert working with remote sensing, and well, and that's the idea to operationalize, but always by taking decisions that are strong, complex, and need many time to be optimized. I would like actually to see the explanation of OpenAI in detail and go how these new tools are solving these kind of questions. That in Google Engine is like from scratch. Many things done, but you have to take decisions. I guess that in these kind of advanced platforms, things are more evolved, and for that reason are newer. And if you want to use, you have to pay and so on. I don't know if you want to add something, because we would like to spend, we have in October, well, with the recent Congress in Bratislava, the International Association of Landscape Ecology, in which we have, we coordinate a session, the same in the Spanish Congress of Terrestrial Ecology. And we have a course in Gijón, specifically on Google Engine for modeling, on which we go with the best experts in Spain. At least maybe we will invite more people. Maybe if some of the remote sensing IT people from here want to participate, we are invited to come to Gijón and participate with us, to go into details, not just in Google Engine, but to go into details on how accurate it is, which are the uncertainties, avoiding the young people to think these tools are something straight. So going into the uncertainties, the difficulties, which are your questions for research, and how these tools can solve you. And the concept is, I don't know if you know it, is translational ecology. It's like we have big data, but we need to know what do we want to achieve. And knowing the final questions in terms of Sonata would be which are that we discussed yesterday, which are the needs of end users. The needs are creating nature-based solutions by using this specific ecological function. For example, the flowering higher than the average of the natural vegetation strip around crops. That's the question. So the first thing is let's create habitat maps. But the objective is not create habitat maps, it's create habitat maps reflecting how some grassland types around crops flowering over the average than others. Because we can use that information for create nature-based solutions that increase pollination. Okay? So the idea of this kind of tools is advanced towards a tool for solving our questions, not a tool for being cool and running tools, because that's good also, but that's not the objective. And we will go into that into the next two sessions. And we have two sessions, one of habitat mapping. We cannot not do many things there, but try to go deeper into this critical knowledge. Another that we found interesting about digital soil mapping. And one question, some questions and thoughts, or is it good, is it shit? So, yeah.
No.
Question about operational cost to Google Engine. So, do you use paid license or free one, or in terms of how much money we do need to?
€0.
0 euro.
For the moment.
For the moment.
Google Engine, if you pay, you are not going to increase your computational capabilities. You are going to increase your storage, data storage. So if you have patience and you have time, run by tiles in batch, because the computational thing is not gonna increase for the moment, as from my knowledge. I don't know.
Yeah, for now, but you know.
So €0. Zero. For the moment. Let's see what happens in the future. And of course, this girl that's working with us is spending quite a lot of time in making these kind of scripts operational. So this was the effort of Gonzalo that we put together to have this analysis. But the code of that girl is like a gold. The half in extension, but it's perfect. She thinks on being efficient, running the JavaScript and changing language if necessary from outside, using the API for making things easier. So we are, and we go from the very beginning, filtering in situ data, up to creating the final, not only the habitat maps, but the reports and PDF following the requirements of Article 17 of the Nature 2000. So from the beginning up to the end, following Google Energy. Everything can be optimized in the middle, for sure. That's what we want to. We are happy being here in Sonata to start to talk in Serbia, a new scenario, not explored from the side of anybody here, and go together to be efficient in using these kind of tools to do things together with, of course, Vito and OpenAO over this to make it more efficient. So yeah, that's the objective.
Which problem we had with the Google Earth engine? So we had the problem with the memory.
Yeah, sure. Yeah, that's a big problem, of course, but that's a problem that we cannot solve. But running in tiles for web prediction, and yeah, that's all. So, yeah, we have one question also, I think.
It was similar to what Petja asked. And here, when you downloaded the data, it probably takes some storage online.
Yeah, that's what you can pay to increase that storage.
So maybe another question would be like, if you want to apply the filters, is the good strategy to download the data and then apply the filters?
No.
Or you can do it like to specify what you want to do and then just generate the graphs.
Yeah, to run the filters on the cloud, for sure. What you are doing now?
So not to use download quota.
No.
But
We don't
downloading the data and then apply.
No. At all. Or you can do the, well, if you have a study site, you can do the mosaic download and run afterwards analysis in Envy or in Snap or whatever.
The thing is that the filtering.
So
has to be done before-
So Jetse, if you want, we can continue, Anna, sorry. Continue, just to stop sharing and.
Otherwise,
So Jetse, if you want to share your screen. Yeah, sorry, yeah, we have time for discussing afterwards as much as we want, but just to allow Jetse to, yeah.
One question, do you have any, like, let's say, workflow how to better to find like existing states and libraries in this?
Yes and no. Yeah. Well,
Of
we
course,
have,
you can Google, but it's.
I will tell you afterwards. So, well, the idea of this first site was just to put a critical view on the remote sensing for biodiversity modeling or for environmental modeling. Once you know that remote sensing is there, we have tools to make it operational at a large scale. Let's jump into how to put together with the environmental data. We will talk afterwards about vegetation and habitats, but we found interesting and thanks, Jets. Do you want to present him? Well,
You know him better.
he is maybe the best scientist I found in my life. In the middle of my life, I found him in a stage of my PhD in Wageningen, and the word uncertainty came to my life thanks to Jetse. He's now working in the Open University of Netherlands and also collaborating with Wageningen with a huge group behind him in the Open University, and expert in landscape ecology, landscape dynamics, remote sensing, and specifically soil. Yeah, we were watching the presentation, Jetse. And soil mapping and soil analysis affecting, controlling that vegetation dynamics, land use dynamics, and so on. Thank you very much, because we were discussing about the soil work within Sonata, and I told him, could be interesting to have an overview of a really high expert profile, even though you have here expert people working in soil, and yet say that we are reconnecting our collaboration to end up with some papers and some things, offered to be here to explain his work and that S-world approach that is quite similar to soil grids, but with major improvements that can give you ideas or improve our lives in Sonata. So the floor is yours, Jetse.
Okay, thank you very much. Yeah, and nice to really be here and to able to present. If there are any questions during the presentation, just we can just do it during the presentation if something is unclear. Sorry for not being there. I would have loved to come over, but yeah, I didn't have the opportunity at the moment. But perhaps we can meet in the future. So as Jose already mentioned, what I would like to do is really establish a little bit the new way of how we are creating soil maps. And I will do that particularly in the focus of, what we need to do is environmental modeling. That's also my background. I'm professor of environmental modeling at the Open University in the Netherlands. And we are currently constantly challenged to create the maps. As a soil scientist, that's my original background. So how do we create the data? And one thing that we also really have to keep in mind is that soils are not constant. Often in the past they were considered to be constant, but there's a very strong interaction between soils and land use. And that also means that if we are going to change our land use through all kind of interventions or through, for example, deforestation or agricultural activities, we are also changing our soils. So that also means that we have to look at a more like dynamic way of mapping and monitoring soils rather than the standard practice of creating a soil map and assuming that the soils in that soil map are there and are constant. So in that sense, there's a lot to be learned. So what I'll do is I'll give you, for those of you, I'm not sure how many are aware of that, but I will just give you a very brief overview of the traditional way how we used to do soil survey. Then I will explain briefly the digital soil mapping techniques that have been developed in the recent past. And really, this has been a major change in the way we do soil surveys these days. And then I would like to focus on downscaling existing soil maps. And for example, in many countries, we have now soil maps available, and you could argue, oh, are we then going to throw them away? No, they are still a very valuable source of information for our new inventories and to keep them updated. So in that sense, there's a lot of challenges and opportunities there. So what's the traditional soil survey? And the traditional soil survey is a rather like interesting process in a way that we say, well, we look a little bit and like what kind of data do we have available in terms of soils and what do we know of a landscape? Often we made a brief like field visit to just explore what kind of soils were there. And then the basis of that original soil survey was to do an aerial photo interpretation, basically identifying units in a landscape that appear to have some way of similar like formation, like a sloping area or a flat area, a river valley, etc., to distinguish those areas. And then basically we developed a sampling strategy of saying, well, okay, where are we going to sample? And that led then to a very intensive field work where we did a lot of observations, and then we drew our soil map. And most of the traditional soil maps were developed in this format. The techniques are also described in the soil survey manual, and it's rather interesting that the whole like soil science community basically agreed on the same like procedures to use for that. But there are a number of limitations, and one of the limitations is if you read the soil survey manual, it says, oh yeah, you have to do 1 or 2 observations per square centimeter on your final map. So what does that mean? If I make a soil map of, let's say, 1 to 100,000, so that is like every centimeter on a map represents a kilometer. So then I have to do 1 or 2 observations for every square kilometer. And you can imagine if you just look at an area of like 25 by 25 kilometers, I just took it as an example here. What would that mean? Well, if I make a soil map of 1 to 250,000, oh yeah, I need 100 observations. But you see that the number of observations you need grows exponentially. In the Netherlands, we created a soil map of 1 to 50,000. And that meant that we basically had to do like 150,000 observations in the Netherlands. And that was really, it took us like 30 years in the Netherlands to do that. And we are a pretty small country, to be honest. And as soon as we finished the soil map in the Netherlands, we basically could start over again. because a lot of changes were made in the landscape and stuff like that. So it was a very intensive process. It also led to a description in terms of salt types, not the salt properties. And it was based on the very stable salt properties. So soil organic matter content, which is varying very rapidly, was there, but it was very crudely included. So yeah, we distinguish the peat soils and the very high in organic matter soils, but really organic matter contents were not included because they varied too much in the landscape. So the salt types were often based on more stable properties like salt texture and those kind of factors. There were discrete units that were identified. So we had a number of observations in the field that were similar, and we basically drew a line around it. And current land use was not included. So that meant that if you had an arable farm or a pasture area or sometimes a natural area, those differences were not included in the soil map. Now, this, of course, was a very intensive process, and increasingly there got a demand from all kinds of different international organizations like IPBES, like UNCCD, the United Nations Convention to Combat Desertification, and all kinds of different groups to really say, well, can't we just map those soils in a more quantitative way? And that's also through, for example, programs of increased agricultural production and stuff like that. We wanted to do that. And we got approached by the Netherlands Environmental Assessment Agency, who wanted really to say, well, we would like to develop a methodology that allows for a more quantitative assessment. Well, at that time I was working for Wageningen University, and we had as a slogan, Science for Impact. So that was always really nice. But there were also modeling groups in the world, like the DSET for crop growth simulation modeling, and Texas A&M, who developed a soil and water assessment tool. And those groups also were really in need of quantitative data. So they said, well, can't we just put our things together and develop a methodology that allows us to really quantitatively assess soil conditions. And the challenge basically for us was to say, well, what do we want? We want to know soil conditions, and we want to have a complete coverage. So we don't want to leave out certain areas. We want to have a quantitative assessment. So we don't want these soil types, but we really want to know, okay, let's say the percentage organic matter and the percentage clay in the soil. We want to have it consistent. So everywhere, well, in this case, in some cases around the world, but also in national databases, we don't want certain areas to be more accurate than others. Well, of course, like anything, we would like to have it at a high resolution and a high quality. And a very important one is the last one, which is based on existing data. They didn't want to go out again and say, okay, we're going to do a survey of 30 years. No, they really said, well, we are now currently with so much data available, can't we do this on the basis of existing data? So there's a lot of things going on. But the starting point, and now I take the example of the global database, but that's also true for national databases. There were a number of issues related to soil maps. And for example, if we look at the Harmonized World Soil Database, which is a global map, there are issues with its resolution, with its consistency and the quality. And just to give you a little bit of an example, this is then the map of the southern tip of India, Sri Lanka, where you see it's a huge country and very big units. So it's not very high resolution. If you look at the tip of Western Africa, you see that one country like Senegal has been mapped at a very high resolution, or a higher resolution, let's put it that way, compared to its neighboring countries. So there's also that difference in the consistency. And also, if you look at the quality of the data, if I just take this map for the whole world and we look at a particular delineated area, a polygon on this map, what do we see? It's, oh yeah, there is a mapping unit, and there's a mapping unit description. There are certain soil types in there. And often what we see is there's a representative soil profile. But here I take like a position, like I think the arrow points to somewhere in China. But that soil type may also occur on other places in the world. And then, yeah, it just like takes one representative soil type for which it then takes the soil properties. So there is an issue of the quality. And to just give you an example of the variation that we have in terms of quality, here I just take some soil types from that map, and I show in the areas like the soil organic matter contents in those units. And you see that for some of these soil types, there's a huge variation in soil organic matter. And we know that soil organic matter plays such an important and pivotal role in all kind of different processes for soil fertility, for drainage, water holding capacity. But if, of course, your soils have such a variation, how useful is then the soil type to really like work with it? So the question is, how are we going to do it then? And at that time, there was already a new development going on. And that was basically that we say, well, look, nowadays we have so much information available on all kinds of different environmental properties. It looks like, if you look at digital elevation models, well, in the previous session, we have seen a lot in terms of land use and land cover maps are available. The original soil maps are pretty good in describing geology and geological variation that we have and the age of different deposits. So in that sense, they are still very useful. And what we basically say, rather than going out and doing like 1 or 2 observations every square centimeter, what we're going to do is we just do a limited number of observations. That's what we call our training data, where we really look in the soil, we describe the soil properties, and then we say, rather than delineating it on the basis of that information only, no, we take all these covariates, all this information on like topography, on climate, on land use, land cover, and we develop a predictive model that then allows us to say, well, if I have, let's say, a certain like geological unit, I know it is, I found it, it's in the use of agricultural practices, it is in a very wet, warm climate, then I predict that it is like this kind of soil properties. And this new technique appears to work really well. If you really say, well, if I have a region and rather than taking like tens of thousands of observations, I take like 200 or 300 observations, often we already see that we can predict pretty well these soil conditions. It does not mean that we basically sit behind our computer and we just do it, you know, behind the computer screen. No, you still will need to go out there and to collect data, but the technique as such works pretty well. At a global scale, going out there and doing all these observations, also in regions that are not like that accessible, so to say, these days, it becomes a little bit difficult. So this works if you have like a relatively small area, then it may really provide you with very good information. And for example, in the northern Spain and Cantabria Mountains, we applied this type of technique, and it worked really well. But we went one step further, and we basically said also, well, can we now do it on a global scale, and can we really apply it in a more basic way based on the soil maps that we already have available? And that is the technique that I will explain a little bit further now, which we called S-World, the soils of the world. And I can share also the publications with you so that you have a little bit more insight. And the Dutch Environmental Assessment Agency, they really wanted to have a description for their modeling efforts that was the basis for the global land outlook. One of these, you have the IPCC report on climate, you also have the global land outlook on soil conditions for the world. And this was used then for that global land outlook. So the starting point here was the Harmonized World Soil Database, which is basically a compilation of all kinds of soil maps for different countries of the world. later, and I'll talk a little bit about it later on, but we also applied the same technique on the national soil surveys. So we did it for Mexico, we did it for Russia before the war, we did it for Angola, we did it for the Netherlands. So we applied it in different other regions as well. Where then, rather than using the harmonized world soil database, we used the national soil survey that was available. Often we used, like in this global system, we used the WISE database, which is a collection of 150,000 soil observations all over the world that was stored. And we used all kinds of auxiliary data on satellite imagery, digital elevation models that were available, climate maps, etc. And basically now what I would like to do is take you through the various steps. So we say, okay, I have a soil profile database. That's core number one. I have a soil map. I have auxiliary data. We put all that in the system. And then the idea is that we then create our consistent high resolution grids on different soil properties that we can use for our modeling. Now it works in different steps, and I will explain the different steps. So here on the left side, you see your traditional soil map. And one of the characteristics of a soil map is that these units are often not described by one single soil type. Often what we know is that, oh yeah, in this particular unit, we have 1 or 2 or sometimes 5 or 8 different soil types that do occur there. So the first step what we do is we take that map and we disaggregate those units so that we have units which are based on individual soil types. So that is the step 1. And then the step 2 is if we have these different soil types, we move to the various soil properties to create this continuous map. So how does it work? Let's say I have an example, and I'm not sure how much you're into soil types, but I just took an example. Let's say I have a soil association, so my unit is described and my soil map tells me, oh, I have 60% Canby soils and I have 40% vertisoils. A Canby soil is just like a weathered soil. A vertisoil is a very specific soil that often is found in valleys. So what we do is we look at our digital elevation model. So here I have just a transect with the elevations. And what we say is, look, if we have 40% vertisoils, we know that these vertisoils occur in the lower and the flat positions. We basically say, oh, we take 40% of that unit and we say, oh yeah, there we find the vertisoils, and in the higher parts we find the Canby soils. And we do this on the basis of elevation, but it could also be on climate, or that you have, like, in the drier parts we have this soil type and in the wetter parts we have that soil type, etc. So this is the first part. So then we have units, and for each unit I have one specific soil type. So how does it look? Here I have a part of this harmonized world soil database. I have a unit, and here you see a unit. Oh yeah, I have 40% of this soil type, 20% of the other, 20% of the next one, and then the 10% of the last one. And we basically take the digital elevation model in this example, and then we say, oh, so now I can disaggregate, and I say, well, certain soils will occur on the higher positions. And you see that there's a strong relationship with it's jumping a little bit on the PowerPoint, but you see that there's a strong relationship between the digital elevation model and then the soil map, which is also, by the way, what we originally find in the traditional soil survey, where we take the aerial photo and the aerial photo interpretation, where we also see elevation topographic differences on these aerial photos. So that is then step 1. So we go from these complex map units with different soil types to a map with simple map units with a single soil type. Then the next step is to say, well, we are going to assign soil properties to each individual, not unit, but to each individual grid cell. Well, how are we going to do that? We basically say, oh, I take the large, like, soil survey database, but on the soil observations. So those are really all soil observations. And we look at the variation that we have within each soil type. So, and we already saw this, this graph. We say, for example, I have here a soil type, and we see that there is a variation in soil organic matter contents, let's say between 1 and 16% of organic matter in that soil. Well, this variation is often not random. We could argue that the 16% soil organic matter content, you will find that under natural conditions, probably in the wetter parts of that region, probably on the one area that has not been used, relatively flat, so there's no erosion, etc. Whereas I probably have the very low organic matter contents in areas which may be sloping under agriculture, there's erosion taking place, etc. So we know already, because of our soil forming factors, what are the causes of that. So if I look at the variation that we have for a particular soil property in a soil type, what do we say is, look, I take my auxiliary information, I look at the temperature, I look at the rainfall, the topography, vegetation, and land use, and I say through a very simple modeling approach, oh yeah, am I on the upper end of that range, or am I at the lower end of that range? And that is basically the idea that we apply. So we look, say, okay, we have that range, and there are a couple of calculation methods. I'm not going to work you through all this kind of information, but there are these calculation procedures where we basically say, on the basis of the climate and the topography, etc., we determine where we are in that range for each individual grid cell. And we developed this model based on an extensive literature review that has been developed over the years. And of course, there's like a lot of different studies that have been carried out. But here there's a very nice review that was done by Guo and Gifford already in 2002, where you basically see, and that's within the red box here, if wherever I am in the world, if I move from a forest to a cropland, in almost all cases, what you see is that you are losing like 50% of your soil organic matter content. And we tried to find all kinds of these type of studies to assess, okay, so what is at the end the effect of climate, what is the effect of land use, land cover, what is the effect of topography, etc. And then we came to a table that gives weights to the, let's say, annual temperatures, rainfall, slope, land use intensity on the various soil properties. And we can say, well, look, certain properties are heavily influenced, for example, by slope, whereas others are heavily influenced by annual temperature, etc. So those are really our model parameters. And that allowed us then to really create global property maps at a resolution of roughly 1 square kilometer. But as I mentioned, how we did it also at the country basis where there was higher resolution. And this is soil organic matter, and then we have topsoil, etc. And these were then basically standard soil property maps. Now the next part is, and I'm started off with that, is now we get, of course, a very interesting part is that we know that there are very strong feedbacks between soils and land use. And that is, of course, particularly interesting. And if you look at whatever soil map somewhere around the world, and you look at some satellite image here, you already see that certain patterns immediately are being copied. It plays a very important role. And we know that soils determine what land use is, because I'm not going to do arable farming on very infertile or very shallow soils, I hope at least. So there is an effect of those soils on land use, but there is also, of course, and we should not forget that there is also the effect of land use on the soil conditions. If I have, as I shown already earlier, if I deforest it, then I will lose certain amounts of soil organic matter in the area. So that is something that we really have to keep in mind. And then we got to this interesting part where we say, look, if I can do, let's say, take current land use and land cover, run a model and get current conditions, then I can also say, well, if I put in natural land cover, what were then the natural soil conditions? Or alternatively, you could even look further in the future and say, well, I have certain scenarios of land use in the future. What is likely to happen with my soil conditions? So this is really something where we say, oh, so if we have the model set up in this particular way, and so we're not just doing the soil digital soil map, but we really do it interactively, then we can also look at different scenarios. So what would that mean, for example? Well, first of all, we could create, let's say for Serbia, a detailed soil map with soil properties, but then we can also run scenarios. Let's say, oh yeah, I'm going to restore certain areas, I'm doing some reforestation or some other like nature-based solutions. What will the effect be on my soil properties? And this, of course, is really important, particularly if you look in the context of, let's say, nature-based solutions, because we have this very strong interaction. Let's say I have drought problems in a region. What am I going to do? Well, probably my nature-based solutions are focused on increasing soil organic matter content. But then I would like to model again my hydrology here to see whether I solve my drought problem. So you already, even with those kind of simple cases, we know that we have to really model the interaction between the land use activities that are going on and the soil conditions. So yeah, I'll basically skip this. This is basically the slide explaining how we assessed the natural NDVI, because that's also something that you really need to know. If NDVI is one of the inputs of our model, then of course what we also need to do is to really say, oh, then we're going to interact there, and to say, well, then we also need, in our scenario, in this case was a scenario of natural conditions, what was the natural NDVI? So there's like an interpolation that we take from our natural areas. And then what in this case, what we calculated at the global scale, and that was also in the global land outlook, maps of the soil organic matter content, the current organic matter content, but also the changes that have taken place over time. And you see, for example, like very strong decline. For example, in India, you see a very strong decline. In some parts of the world, you'll see a very strong increase of soil organic matter. For example, the Nile Delta, yeah, it's too small on this map, but the Nile Delta, where you really see an increase of soil organic matter contents. So that is the procedure that we are developing, and basically what's currently is the situation is that there are all kind of other initiatives were developed in terms of other global soil maps. So there's like, for example, soil grids, etc. Those are the specific characteristic of those maps is that they are a one-time assessment, so they don't do like the dynamic modeling as we are trying to do it. But of course, it's like almost like a validation study to see how do these different maps compare. So we also included like a validation, which at this scale is very difficult, but to compare the different maps. So the idea is, and that is also what I would like to propose, and what we also could perhaps contribute to the program, is to say, well, look, for a country like Serbia, but also we did it, and as I explained, for other countries, there is like a soil map available, and we have this soil map, and we have these conditions. And often, in some cases, not all of the countries, by the way, but in some cases, and I think this is also true for Serbia, there is a database on consistent like observations of soil conditions in the country. And that can then directly be applied to this soil map using the S-World tool, so that we then get automatically, almost automatically, a high resolution soil map for Serbia. We did this for other countries, as I mentioned. For example, for Mexico, they had a very unique, I would say, situation where, as part of the global monitoring on carbon stocks, they started 10 years ago already by doing every so many years, I think every 4 or 5 years, they're doing 10,000 observations throughout the whole country and really observing that. So that gave us a very good starting point for all of these soil types to also determine, okay, what are the ranges of these soil properties for all of these different soil types. And as a result, we were then able to really disaggregate the soil map. So it's a very straightforward procedure. It's not like we're talking here about high tech, high fancy, very complex modeling, which is considered by us at least also as a big advantage, because the procedure as such is very transparent. It's directly recognizable rather than some of the AI techniques where you don't know how the value was estimated. In this particular case, each of the values for each location, you can directly say, oh yeah, this is because this soil type gave me a range of, let's say, 2 to 5% organic matter. We were very high, relatively speaking, in, let's say, the NDVI. We were perhaps on a relatively flat area, etc. So we really know why it is estimated to be like that value. And that for us is, I think, a very strong point, particularly when we discussed at these national databases. We discussed it with the national scientists, because you can then really say, well, yeah, well, in some cases, to be honest, there were some national soil scientists who said, well, yeah, but this can't be true, because I know I've worked there and this value is not correct. And then we could immediately say, although there's of course a lot of critics on modeling and stuff like that, but we could immediately say, well, look, let's have a look. And if you then see, oh yeah, but in this particular area, the soil type was classified on the soil map at Chernosem. And of course, the soil map doesn't have to be correct, but that was at least the map. We had the different auxiliary data. So we could really start that discussion. And that was, for us, really valuable. And yeah, of course, you can then have all kind of discussions. Also, if you talk about nature-based solutions, the introduction of those, certain land use change trends that are occurring. So what is causing the changes that are being modeled? So that is in a very brief overview what I wanted to say. So it starts with the traditional soil map, where we basically just have to go out in the field and do a huge number of observations. We went through a new era where we say, well, we're now using digital soil maps techniques, which are currently still a lot of cases developed in a very efficient way, as I mentioned, particularly for those areas or those scales where you don't have an existing soil map available. So the soil types are basically not mapped out. But in the case when you have already a soil map available and you want to take that as a starting point, then the SWORD methodology is a very attractive procedure, because particularly you know what you're doing, you're making use in a very efficient way of all the information that is out there, and you can do, to a certain extent, dynamic modeling to evaluate what will be the impact in the future under different scenarios, or perhaps even looking back, but that's an alternative. So that is basically what I wanted to tell you. I don't hear you at all, but.
Yeah, sorry, I was touching the screen, making draws around the presentation.
Yeah, no problem.
Thank you very much, Jetse. Do you have some questions? Tiana was. Thank you very much. Questions, Tiana has one.
Yeah, I thank you very much. Thank you very much. Thank you very much. Basically, I wanted to say something when you were talking how this can be used to learn more about the trade-off between converting something from arable to natural land. And basically this SONATA project we are working so this SONATA project has the aim to map habitat types and to develop a soil map. And basically, we would like to connect the quantity of trapped soil organic carbon in different habitat types. And we do have this traditional, we did have this traditional mapping survey. We do have this atlas data, let's say, about the soil types. And I'm not sure, are we using the same one? Because we have this one for the northern part of the country that we use now. And recently we have checked reliability of this map and uncertainty with the measured data from the In Situ sampling campaign. And I would ask Branko to help me if he's still here. No. Peja, do you know the results of this? How in the range of how would you say how the results we got from the In Situ campaign are matching with the atlas data?
Okay. But results are not good.
Okay, yeah. Okay, so like just before Peja answer, I would like to say we would like to develop the soil map for natural habitat types. And what we do have here, we have this map for the arable land. In the end, implementing nature-based solution and optimization, spatial optimization, where to introduce them within agricultural settings should take into account this change that Jets mentioned. Like you need to take into account the potential change in the soil characteristic and to say, yeah, go for this. This is good. For this much you will contribute to the mitigation and so on. And this will help pollinators because the main ecosystem services we are targeting are food production, pollination, and soil organic carbon as indicator of the soil. So could you please tell us something about the discrepancy between the map we have and the measures we did?
Okay.
Yeah.
So maybe to explain Vojvodina and composition of it very simply. Basically, we have over 80% of agriculture areas and some forest or mountain that we have one. And basically, that's all. We have some pastures and problem with the soil sampling that are conducted in Vojvodina is basically most of soil samples are from agriculture areas. And in this project, we are not interested in agriculture area. We are interested in small isolated parts of Vojvodina where we have natural and semi-natural land. And basically, in most surveys, those points were probably didn't take in the account. So in this kind of sampling issue that is obviously not suitable for our case, maps that are produced doesn't have good result for our problem.
Yeah.
And we need to develop the one, but we need help with that. And like, let's try to. I really thought that Branko will be here because it's like, okay, so. We are missing the key person who was like working the most with the data now, but basically we can arrange the meeting and that's why we wanted, that's why we were talking about having you here. But anyhow, we should, so the problem is that, not the problem, but something that we would like to produce is the current state of the soil that will be also connected with the SONATA made habitat type maps, in which you will have information what type of grassland is there, not just like it's open grassland area. It's going to be like steppy grassland, and then we have this measurement of the soil within those areas. Not that much, but we have some, and we should combine everything possible to get this map, and then to try to simulate what would happen if this unit will be allocated to the for example grassland. Because we are really planning to support pollination and yields and so on in the monocultural area.
Yeah, but perhaps to react on it, I think it's a very common problem, and I think what is happening is two different parts. One part is that we see that the soil survey, as the results are presented of the soil survey, they do not correspond with the actual kind of data that we find. This is something that is very common. And for example, in the Netherlands, and if you look at the soil survey manual from the US, there's a tradition. It's kind of opposite from like what you are saying, because there we often say what we would like to do if we take a representative soil profile. The representative soil profile is often under natural conditions. So it's exactly the opposite, but it's still, if you look then at soil databases where we have like soil observations, it's often under agricultural land because that's where things have been sampled, etc. But for the soil survey itself, it's often under the natural conditions. Now, what does it mean? First of all, it does not necessarily mean that the soil map cannot be used because these soil types are still like correct. And in terms of like the soil texture and perhaps the profile build up, it could still very much work. The element that does not work at that moment is the estimation of those ranges. Because if you have the ranges being estimated, let's say at the very low end, because the sampling was done under arable farming or on the arable land, then and there are no like data included on the upper end, let's say under natural conditions, then yeah, you will need to have some level of like assessment to say, well, yeah, the real values go up to a higher level. That could mean that it requires some additional sampling in these natural areas, and then we can use that to correct. Or we can, and that perhaps in an initial stage, say, no, we know that the sampling took place under kind of agricultural land, and often like when the sampling was done, it is registered what land use was or land cover was. So we can correct for that, and then we extend the range based on what we expect. So there are different ways to do it, but I think to really answer your question properly, I think we should really sit down once together, and perhaps we can do it in the coming weeks, some moment, to really say, okay, so what is the situation? How do the data look, and how can we establish that?
Okay, thank you. That would be great.
But one comment that goes to the beginning of my PhD. Well, when we started to talk with Jetse, and I met him, the interesting thing was, in fact, to go into natural soils, not Jetse, because he found and his group very interesting to start deepening into what happens with the disturbance, eminent forest, and secondary association afterwards starts to recover. And we did that job in the different places, 2 different places in the north of Spain, and the results were a success. In fact, one of the properties that we found in that soil mapping was the most important driver in identification the distribution of vegetation types. So, well, yeah, and as Jets said, always a matter of correcting by applying theory or applying observations.
Yeah. Okay, but that, yeah, for sure we should meet. But thank you. But that's exactly what happened. We had this problem in ranges that we,
Is this map available somewhere to access to see to?
Sorry, I didn't hear you well.
If the map is available, that map that you are showing, or which kind of map is?
No, this map I just took from the internet for my presentation. I don't know whether this one. We have maps of Serbia included from the European soil map, but I know that there is also a detailed soil map for Serbia available, but I don't know where to find that digitally. I have a print of it, but I don't have it digitally.
Yeah, I saw the PDF he sent. I saw it, but I couldn't.
Yeah, the first task is to, as we talk with vegetation and land cover, is just to check which information is relevant and put on the table to start training from that.
Yeah. Perhaps.
Okay, so Maya, you have a question?
Yeah, Maya, yeah.
Yeah, I'll come closer.
Yeah, sure.
Thank you for your presentation. This was very informative. So my question is, in Sonata, we have 2 case studies, sort of 2, let's say, experiments set up. And one of them is the pollination limitation experiment in sunflower fields, where we want to see that which is the influence of the area and the type of the surrounding habitats on pollination or yield of the sunflower. And so last year we did the soil sampling, and we plan to add additional soil samples for the locations of the experiments, where we want to check for the organic carbon content in the soils to sort of say that, okay, if we add more, let's say, some type of semi-natural grassland here, that would inflict a higher abundance and maybe diversity of pollinators, and that would influence the sunflower yield positively. So this is like a revitalization of grasslands, right? And then for sure, we maybe can't say that the revitalized grassland will have the exact same carbon content, organic carbon content as the one that we have now, that we have sampled. So some of our colleagues argue that we can't say that, hey, if we revitalize this type of grassland, the carbon amount would rise and this would help the pollination. But in your case, since in Sonata, we don't actually plan to implement anything, this is just for modeling and scenario testing. Is there a way that we could actually do it? Should we correct the values in some way, or do you think it's not a way to go? Thank you.
Yeah, well, perhaps two observations. First of all, I think certainly what we can do is to have a look at in what range can we expect changes to happen. I think that's a very important starting point, because the risk, of course, is doing the measurements is that we are talking, particularly if you go from one year to another, the changes that you will have are relatively small compared to the natural variation that we see in soils in carbon contents. So measuring differences and changes as a result of management within 1 or 2 years is often very difficult. So there are two ways how to deal with that. One is to say, well, I'm going to look, and basically what they say is then we are convert or do like the trade-off between time and space, where we say, well, what we are going to look is for areas that have been under treatment 1, and we look at areas that have been under treatment 2, so already for a longer period. But I'm not sure whether that's the case, that's possible in this particular case. But certainly I think what we can do is do this like assessment of what is the potential. And that already is a very good starting point in combination with your observations that you have done, right? So the 1 time or the 2 time, but that doesn't matter that much. But then you can really do it. But I think this is also something perhaps we should have like a further discussion on it on the sampling design. But I think it should be possible. Yeah.
Thank you. Okay, but then we may be in the case to add up additional samples to those that we already did last season, and it would be great to meet up with you and to showcase you what was basically we follow the Lucas, and then we use the soil-borne protocol for selecting sites within locations. So we're gonna explain it once we meet, and then maybe if it's possible to help us, like if it needed to add new samples to this case study area, because we did landscape scale soil sampling, and now maybe like focusing on certain areas maybe we should do more, I guess, but then we for sure need to meet.
Okay.
Yeah, one thing is, just as a final remark, one thing is, and that's also really in the design of how you do your sampling, never sample in those cases at one location, but take a composite sample. So take multiple samples throughout the field, mix them together, and then do the analysis. Because then you're taking away the short distance variability, which is bothering us take while we're dealing with the monitoring of carbon contents.
Yeah, we did it. We had like three at each location. We had 3 plots, 30 times 30 meters, and each plot was
9 sampling points.
Had a nice sampling points. Like it was a composite sample, and and we can expand it additionally because they are all part of the clusters of habitat types and so on. But it's like it's gonna take a lot of time. We are just
good. Yeah, but let's meet up one of these days, and I would love to discuss it further. Yeah.
Okay. Thank you very much.
Okay, so Jetse, thank you very much as always. Because we know you have a meeting at 1, so not stop to take the lunch at the Dutch time. Come on. I hope you did it before.
Yeah, that's okay.
Yeah. Also, thank you very much. We keep in touch.
Yeah, it's a pleasure, and looking forward to work together.
Okay.
Thank you.
Thank you, Jetse.
Okay. Bye. Thanks.
Bye.
Can we put this on board with lunchtime as well?
Yeah.
Yeah.
So now So thank you, Jetse. So one trade-off to all of you, feel free. I really like to that Jetse told it before, because he was talking about single approaches that S-World, that you know every single step. That's what we told when talking before and yesterday, and from now on, with what to do with in situ data. We're talking about visitation and habitat mapping. Doesn't matter if we use Google Engine or whatever, in artificial intelligence with I don't know which kind of algorithms. But what we need to know is that the connection between the in situ data and the predictor's behavior is perfect. There are two pieces of the puzzle that communicates perfectly. You cannot put information that you don't know the uncertainties not against, but in front of information that you don't know the uncertainties, and let it go the algorithm to create things that you don't know what is going on. So what we do is to put together in situ data plus remote sensing, time series modeling, and so on, but always using one word, this data, we call it data curation, this data refining, cleaning, whatever. That allows you to understand as an expert that the two worlds talk the same language. That's what Jetse told, that we have maps, we have samples, we have predictors, but we know what is going on. I saw many times ago that graph of a mountain with cambisols, vertisols, insectisols, and you know clearly that if I have an association, a soil association, the cambisol will be in the slope, and the insectisol will be in the flat area. So it's exactly the same with vegetation and habitat mapping. We have to put together both worlds to refine what is going on in both worlds. We cannot get in situ data that is not aligned with the remote sensing, and we cannot get remote sensing information that is not aligned with in situ data. So I have one presentation talking about this with images that is better, and then I have exercises of hand-on for running in the GIS and explaining you how things going. But we can just do nothing, eat and go, or we can just spend 15 minutes for the presentation to put colors to this comment, because once we end up with in situ information here in Vojvodina, let's say at the end of July or something like that, we will have to run specifically this kind of analysis. And I think that will be very informative, that we can run all these analyses that I can explain you today all together. Not just take the information in our site, run and give you another data set, and you say, okay, one data set, another one. You understand that we refine the data, but you don't know actually how. It would be very interesting to run the analysis of refining together for creating a second data set that is refined by using remote sensing. And that data set is the one, even though we can run analysis now with the EVA database and explorative manner, that's good. That second data set will be the good one for creating the final habitat maps for SONATA, for taking decisions on whatever, at different scales, for the whole Vojvodina, the whole Serbia, just the specific areas, the strips around crops, doesn't matter. We have to work with the in situ data to refine. That's what I wanted to tell you, but the concept is this. It's just in situ data, remote sensing, put together and refine. We created a conceptual framework. That's what we are going to publish now to meet a high-profile journal. But it's just the concept. Then touching the data, we will have to do in SONATA, and we can do it together, maybe using a hackathon day, a couple of days. Just first step, you can explain how data were collected. Next step, let's, with 3 words that I have in my presentation, cleaning, filtering, and refining. That is a concept. It's like the consistent services. We put names, regulation, the 3 types of consistent services, the production and culture or whatever. It's just putting names. But we have the concept, and running analysis, I think, could be not done today, spending 1 hour running the exercise I put there with the points of the Cantabrian Mountains that we are running now, but do when we have the data. For not having you all here 1 hour more after lunch. If you want, you can decide, we can go to take the lunch, come 30 minutes, come 0 minutes, or if you want, we can come 1 hour and a half.
Just let's have a
Yeah, let's have lunch.
Yeah.
And then I guess if all of you are interested in the second part, we can stay. If some of you are interested, we can stay. And if no one is interested.
Yeah, we can start with 10 minutes presentation I have for putting maps and colors to all this. Then we can open the GIS and just go through the folders that are the result on all this, putting together SDM, habitat mapping, and so on. And yeah, that's all. What we have also is we created one slide mock script for trying to, and you have there, to everything that we have been talking about today is summarized in one Word file or one page. And that's the philosophy of the mock course, is to have one bill that summarizes everything that we can talk in 10 hours. And it is there.
And we would like to have you for the second session as well, because now you're here and then who knows when you come back. So while we're here already,
we will be here.
Let's do it, yeah.
Okay. We will be here. I don't know if you have more things to do and we can just do it briefly or not, whatever.
Okay, so then lunchtime.
Nice, thank you. So Marta,
It's possible to.
So this will be like a bonus track for, like, in the concerts is done everything, but we can extend this as much as you want. But as I told, the good thing is that we will go through some ideas now in the presentation. Should move, no?
I think it's turned off. 1 second.
Or something is moving with him. Isn't this normal?
No, it's fine. Just
Oh yeah. So the good thing is that we will go through this concept of data refining for vegetation mapping once the data is collected. We were discussing yesterday the protocol. The good thing also is that more or less after a discussion, it was very nice because we found like a common way, a unique way to go through the minimum that we need to do this year in the data collection in the fieldwork with Sonata. And we can just open that approach to the maximum this year, or we can just do not the minimum, but settle the basis of everything this year, and the next year going into details of the maximum. The difference of the common and the maximum and explaining is what I told before. The objective of this task is habitat mapping, is vegetation mapping at the very detailed level of classification topology, units, level, whatever, and the crosswalks to Annex 1 of the directive and so on, the habitats that are included in the directive. And so it's creating that map for the entire Vojvodina or Serbia or whatever. That's the common, like the minimum need we have to achieve this year. That map will be validated and refined and improved and so on. But the maximum is, which is the purpose of that habitat maps? So why we are creating habitat maps in the Vojvodina region? And the objective is not creating maps and having a map with colors and put there and have a paper. That's one objective, secondary one. But the real objective is to use that habitat map to put together with talking about Sonata specifically, working package 3, to look for nature-based solutions that improve the ecosystem services we want to enhance at the level of pollination, carbon sequestration, or whatever. So the habitat map is a tool that will inform us in a spatial explicit way across the territory where to take decisions and which decisions. So mandatory since the very beginning. I have this clear because it's common sense, but also because I've been fighting quite a lot in the last 10 years, working in Nature 2000 in Spain and in different projects across Europe and the world with the stakeholders. So if with the information that you create does not satisfy their requirements, you are lost completely. There's nothing to do because they don't mind whether you spend 4 years in the field or 10 years learning remote sensing. If the information is not enough for satisfying their needs and the spatial pattern of the results is not good for combining them, you lose the engagement. So, of course, the good thing in Sonata is that we have, and we discussed yesterday with Tian and Maya, we have 2 years for doing this habitat map approach. So we can do 2 things. Just go for habitat map the first year, do our best, and then go to the specific locations on which you are going to work with the pollination or whatever, and to see the habitat map, understand which improvements we have to apply to that habitat map, more typologies, because imagine that we have UNI's habitat type is a grassland, but we need to identify where that grassland habitat type is able to have more flowering for aiding pollination and so on. So it's not enough mapping the Arenatherium grassland habitat type is the UNI's, I don't know now which one. We need specific indicators to go deeper into the area map as UNI's level ADC to identify where that UNI's level have more vegetation production in May, which imagine is the key indicator that will allow you to have more flowering because the vegetation increasing in May is like the key starting point of having more flowers in one part of that habitat type or not. So that refining of vegetation mapping not only has to do with in situ data collection, but it has to do with which in situ data collection we have to collect for getting the final result we need in the habitat mapping process. And that discussion yesterday in the work in the afternoon, very good, allow us to have like a roadmap to do both things. And now it's on the roof of Sonata, and you have to discuss or whatever to decide if we can just go in the field from this year up to the maximum for specific locations, do a specific effort for collecting more in situ data for allowing to advance the habitat mapping into the refining of that differentiation across one habitat type in structural properties, functional properties, the absence of specific pressures. We have a project now in alpine grasslands in Spain, and the main factor destroying the grasslands is the grazing pressure. So for us, we want to map the presence of grazers around that specific areas to include as a predictive layer of the ecological status of the habitat type. So what has to do one habitat type and in situ data collection with the grazers? So it's mandatory not having grazers for preserving some specific habitat types or wetlands and so on. So understand this as an in situ data collection effort that try to respond to specific questions, and that questions will be motivated for the final objectives that we want to achieve. So it's not enough to have in situ data. You can have in situ data, for example, when we receive the EVA database, we can think, okay, it's done, we have EVA database at all. When we receive EVA database, we have to criticize quite a lot EVA database to find the spatial gap, the typological gaps, to find, even though we have habitats through the whole Serbia, imagine, and the whole, all habitat types distributed across the whole Serbia, we still can have biases in the data collection because of different reasons. So we have to analyze the in situ data, and then the crosswalks is not straight. So the relation is one to many, sometimes many to one. So it's not straight to change units to annex one and so on using crosswalks. Then this was the main issue of this, the first classes. The spatial predictors, remote sensing and others, as Jetse explained, we have to criticize as well. It's clear now after 2 hours talking about these amount of things that we can do with remote sensing. So it's not done to move to more. So the question is not. We have to theoretically, and I think that's in a project like this that it is meant to boosting capacity for me the main keyword is what I learned from Jetse is the uncertainty. Everything has uncertainty. We need to know how to manage that uncertainty. And the way of doing that is just, I like the expression of looking through the window. You can see a heterogeneous landscape that vary from the mountains to the coast, but not only heterogeneous, but also dynamics that change over time because of driving forces. And everything is heterogeneous, everything is dynamic. And that heterogeneity and dynamic nature of landscapes and ecosystems is absolutely context dependent and vary from one point to the other. That's something that we just told we sometimes forget if creating results that are not dynamic themselves. Well, we can create a very good map of Serbia, but if all the effort is focused on in situ data collection and then to extrapolate, once we have a big disturbance in some area or after 10 years, maybe that map is not useful. We have to take into account dynamic system of the information, because we want to relate that biodiversity to the ecosystem services, regulatory, for production of benefits, cultural ones, whatever. But everything that has to do with ecosystem services is supported by that biodiversity. So how creating that information from biodiversity to support ecosystem services? We need maps. But again, we can go to Copernicus and we can download many maps from Copernicus that maybe is not useful because of the spatial scale, temporal scale, and so on. What is clear is that we need spatial data, and Copernicus, as Anna explained, can provide us quite a lot of data. If you don't know Copernicus ecosystem, we encouragely tell you that explore the webpage, in this case, Copernicus Land. You have many information there about many different things, riparian zones, imperviousness areas. This is the product N2K. The N2K product is a specifically product of Copernicus for Nature 2000 areas that was developed in 2018. And we got a contract for the Environmental Agency for updating that layer. Now it's called Protected Areas for the entire Europe. There is a gap in Serbia, unfortunately, but it's very good running Sonata in this moment, because there will be a very good opportunity to communicate with the Environmental Agency once Sonata was done, because you can have one tool, even though it's not good for the nature-based solutions you want to apply in these pilot cases. That will be a very good opportunity to engage with the Environmental Agency, Copernicus Land Monitoring Service, telling, okay, you have one product, Serbia is not included, but come on, look, we have, with the same approach, we have information from Serbia. Well, that's an idea, just dreaming. And also many information from Copernicus, and that CLC Plus backbone and instances that appears now. So Copernicus and the remote sensing have a lot of opportunities for applications, for applying different indicators. There are quite a vast literature, getting information. And of course, we can create our own maps. We can download from Copernicus, but we can use satellites. We can create our maps from now, from the past. So what we did in the beginning, for started to work with habitat maps, was to do what we discussed yesterday. So we have to create habitat maps for Vojvodina. So we should not start from scratch. We have to use the previous information that we have as good as possible for setting this thing. So, how to explain this? Please interrupt me and say whatever. But what I want to say is that I started talking about looking through the window. I need to map the reality, and I need to map the reality focusing on specific objectives, supporting biodiversity, supporting with our biodiversity the ecosystem services. And I need to map that because I need to include in my spatial analysis and whatever. But I cannot start from scratch. I have quite a lot of spatial data there. And in such a way that if that spatial data fulfill my objectives, for example, yesterday, we discussed using Korean land cover, because maybe it's the best land cover map that you have across the whole Serbia, or that translation of land use land cover into your crop maps and so on, to stratify the territory a little bit and say, okay, maybe it's not the best map in the world, but we're going to use to stratify our sampling efforts, or we are going to use to exclude from my analysis the agricultural areas, because now we are interested in natural and semi-natural areas. So that information needs to be included in our equation. If we have not such information ready, maybe it's not the best option to start mapping habitats from scratch neither. Why? Because imagine you want to map, think on, if some of you is used to work with vegetation, think on UNI's level 4 habitat types of grasslands. It's quite complex even for a botanist to go to the field and to say, okay, I have this community, I have this other community. And even though that's possible, it's very difficult to have a boundary to say, great, from here, I have this habitat type, and from here, I have this other habitat type. And what happens, and that this comes again from our experience with the stakeholders, is that you do your best to map the habitat types, and you finally, yes, I would put my salary in the next 6 months on the table to make a bet here and I will win. You will make omission commission errors between grasslands and forests, and between grasslands and shrublands. If you map directly the habitat types, it's very difficult to separate even simple categories. Very, very, very difficult. For that reason, after years and years and years working with this and planning with stakeholders and trying to engage this habitat mapping your remote sensing into the Nature 2000 monitoring and reporting, we learned that we need to apply some kind of hierarchical protocol to be efficient. And the hierarchical protocol is first use the map I have. If they are good, or if I have not another opportunity to do something better, I will take that map and I will stratify using simple land use land cover categories. For which reason? For avoiding making this stupid error of try to map different types of grassland, and at the end, confounding one grassland area type with one location that actually has a forest. Come on, that has no sense at all. And if we apply the living lab approach, that is engaging with the stakeholders since the beginning, that would be not acceptable at all. But if we move to land use and cover, that is, let's say, easy, is something easy with a small legend. The legend in this map is basically this one. Is broadleaf forest, broadleaf and coniferous forest, scrublands, agricultural land, pasture and meadows in the valley bottoms, bare ground, rock outcrops, urban and anthropic territories and water. Something very, very similar. So what we did in our region, we were thinking about using Corinne land cover, but in Spain we have better maps that Corinne land cover. It's our national land use land cover system is better, and we compared both. But when comparing both, we found still problems. So we decided doing our own land cover map of this is the region of Cantabria when we were working with Ana in the Institute of IS Cantabria. And because of the engagement with the regional government, we were invited to participate in developing the technical basis for the plan of the territory management of the region. And the first step was just because of this speech to the government and GIS working in Nature 2000 to create a highly detailed land use land cover map of the area. For working afterwards in the habitat maps in the same way that we are going to do here by using Corinne land cover as this. I showed you this example because I was very happy to work in this. We were very happy to work in this thing because look, this is the map that we got for this land use land cover map. This one, when you go into detail, we were able to do this. This is the auto photo. This is the map. So the different colors are vectors. So this is a typical land use land cover map that we created at 1 meter of spatial resolution. So you can see the level of detail because we were encouragedly, the government wanted to have something that was almost one-to-one in real. Even every single tree was mapped because the nature-based solutions they wanted to apply in that plan of the territory management needed to account even for one single tree in a park of one city. Using this approach, we afterwards map people in beaches, we map cars in the parkings. So the level of detail is quite high. When we had that map, we told, okay, which is the best map we have in Spain? Like Corinne, we're going to use Corinne here, but which is the best map we have in Spain? National Forestry Map is the best one. National Forestry Map is in this side, and this is the land use land cover map that we did in collaboration with one of the best experts in GIS we have in Spain and in the world. He's called Gabriel Ortiz. He's very famous. When I was young, talking about science, I learned English with a photo. It's a photo for Spanish people called the photo de Gabriel Ortiz. And this is that guy. So it's amazing. If you think in technology and GIS technology, that guy can implement. And we were just doing the hard job, collecting samples and so on, and he helped us to implement that thing. So forestry map and our map. So the differences are amazing, even though the patterns are the same. The differences were amazing. And doing that, we thought, come on, and why we are not doing that for now and the past? In Spain, we have orthophoto from 1956. So we applying, this is a deep learning technology from ArcGIS Pro. This is the deep learning technology of Esri. We applied that technology. It's not new. It's an old artificial intelligence technology, old 5-6 years old, 7 or something like that, TensorFlow. So this is the map of 1956. in the right. This is the current map. So we identify the areas on which the forest is expanding for applying the nature-based solutions because of forest maturity and so on. So I show this just not for saying, look what interesting things we did, that also it was very, very good. But I show that because that was the key for telling to the stakeholders, we are not failing when making a separation from forest and shrubland and grassland and so on. It's done. We are not going to be worried about where is a forest, where is a shrubland, where is a grassland, where is whatever. We have the key for doing that. It is impossible to do it better in this moment. 1 meter of spatial resolution, validation with 25,000 points we got from the field, botanists, other maps and so on. Validation was around 98%. And when the points were telling us classification was not good, it was problem of the validation, not problem of the map. So it was almost perfect. So we are not going to confound never. Forest, shrubland. So what are we doing afterwards? We go already to answer the needs of Nature 2000. But so this map is not advancing. It's not giving the solution to nature restoration law, whatever, in restoring or preserving for nature-based solutions. It's not going as the solution for the Habitats Directive, but it's going as the perfect engagement with the stakeholders. Because of this, now we have new contracts with other autonomous regions to work in Nature 2000 because we are not, in the beginning, we were selling like a dream. We can map with remote sensing everything. Okay, oh, it's good, you can map. Then when we send them the maps, they told us, come on, you are confounding grassland habitat type and forest habitat type because the models are failing. Sometimes similar, we have similar reflectance in a really productive grassland and in a young forest. And at the end, what you are using is the reflectance. So if we don't use a spectrophenology, we can make errors. Well, the issue is that we have such requirements, and I really love this paper. It's a science paper that is telling us that we want to take care of our world by using biodiversity data, but that biodiversity data is not well shared across the world. Some regions has data, really bad data. Other regions has no data. Other regions has very good quality data that's not homogeneous across the space. So we need to balance that quality data for getting a more homogeneous world. First of all, talking about the environment, but afterwards talking about everything. That's what I'm told. The good thing on Copernicus is that maybe it's not the best data that we can collect, but it's homogeneous data across the whole Europe. So this thing that we can do in reality is creating a shape that I have the map, it's done. It's not enough because we need to improve our maps. And which is the way of improving our maps? Going to the field and collecting more field data, having reliable field data for all these things that I am talking about. It's nothing to do with the habitat mapping. It's just like being clever and being organized properly, what the tools that we have for starting working in habitat mapping. And once that is understood, that's in the conceptual framework that we are now writing to submit to a paper used in Turkey. But it's the basis of the conceptual framework of task 1.1 that we would like to put on the table to work in Sonata. Even though we afterwards model whatever, we do whatever, but to say, okay, in Sonata, we know what we are doing, capitalizing knowledge of many years working in these things and facing and going against a wall that are the managers and the stakeholders of one place that they don't care about botanists. They don't, in our place at least, they care about their needs, and we have to fulfill that needs. So in that way, we go deeper a little bit into the what are we talking about? We are talking about data refining of in situ data refining for modeling. So there is a wall in between. I mean, I'm looking at you because you are here, the most botanical profile I know. But you are in the field collecting data, and we are in the remote sensing side creating models. So that's a view that is not real. We have to eliminate that wall because we have to put together by making a refinement before modeling that allow us having coherence data for extrapolation. Other words, we have that wall, that this is the wall that exists, at least in the traditional way of understanding remote sensing and spatial modeling. This is true, and this is a dream. This is imagination that is not true at all. and that's not like that. And the thing of doing that is going to the field. So we have to go to the field. We have to collect the information with coordinates, with the real. We are talking now about the field. We go to the field, collect information, units habitat type, and each one. But afterwards, we need to couple that information with all that digital predictors, that remote sensing as well. And this is one of the things that we have to solve as soon as possible, is that tool for putting the data collected in the field into digital format that you have experience in doing that. And we have to talk, because talking yesterday, we have a very straight, easy approach that it can works, is having codes for coding what we see in the field, using your tool that is already working, or we can use the QGIS, we don't mind. We did in Turkey this with a company, I think it was a Serbian company called Oikon, I don't know if it's Serbia, I think.
From Croatia.
Croatia, okay. Oikon was working with us in Turkey, and they created this ad hoc for us, but now QField and maybe your tool is enough. That allow avoiding this kind of this thing, this word that I like, this word, the worst word in my life, and the best one is the answer.
Sorry to interrupt you.
No, yes, sure.
I'm going back to this tool again. So this tool that will be prepared by Gonzalo, and which need to add these options based on the criteria we decide to follow as well, aside the type of the habitats, will be sent to us to be installed on our tablets, or how you have any agreement on that?
The most important thing on this is to define what the first thing I was trying to explain, what are we going to collect in the field? You need to define that.
That's
at least in an Excel file.
Yeah, I know. That's what we're gonna do. But then the next stage is like you integrate that in that tool and you send it to us to be installed, or what's the plan?
Once we have the list of information that we are going to collect, you or we have to decide if we go to with your app, the one with the picture, location, and space for comments.
Yeah, I know, but yeah.
Or we can use the QGIS tool that is just a tool available to download and put in a mobile phone, in a tablet, or wherever. What we have to do if we go for the QGIS tool is to that list of information you are going to collect, to prepare to be included in QGIS. That is, Gonzalo, correct me, is not so complex.
No, it's easy.
Yes, it's easy. And the other thing I think is quite clever, and we can also do both, and afterwards you have both on the house, is just to code the information that you are going to collect. Imagine you go to the field and you first collect the unit habitat type. You have the code for 4 characters. Then you have a comma. You just write down in your app a comma, and then collect. You have to code and to agree on that. We're going to collect one indicator of structure of forest, and you quantify that structure, that indicator, from 0 to 9 in the field. So you put one number and another comma, and you repeat that for any single indicator that we agree to collect in the field. What you're going to have in your tool is a comma separated file that you can import directly as a save file in a GIS afterwards. That's very straight, simple, and easy and effective. The other way is, as you were, the thing that you were talking, is having the QGIS tool that you have the mobile phone and open like a tool, and you select, instead of writing the code, writing the number, you select.
But you cannot in the this app Dyson has, you cannot add like 100 something habitat types, like the many to.
No, but you write the code of the habitat type.
That's okay.
You write.
You write, and
D615.
in your app you can select.
In the app you can select.
Okay.
It's a way of matter. You can talk about that.
Okay, we can talk about it.
Yeah, sure. So the decision yesterday, the meeting was so productive. We have like options for everything. That's good. Very nice.
Yeah, and Jose, this tool that you and Gonzalo are like preparing for us, the data you collect go directly to somewhere, or
you can synchronize afterwards with. I know you can do in ArcGIS. I don't know if QGIS.
Yes.
Yeah, no. Yeah. We worked before with ArcGIS.
Okay. It depends on so we need basically the criteria, the selecting criteria, you need to add them up, send us tool, we install it, and we will see whether we're gonna send it to the server or we're gonna keep them and then copy.
Yeah.
Okay.
In ArcGIS Pro, you can connect to the server in ArcGIS Online, and everything in real time can be seen by an analyst.
Okay.
But it's something to once decide the list of things to collect.
Sorry,
Sure.
we have application that is
Pa
very.
sad je objasnio, zato što to je, I'm gonna do it in Serbian.
You have the comment, so but I also talk.
Okay, sorry,
Please let
just
me finish.
go in English.
Okay,
Yeah, that's
you
good.
also in the comment of our application can put the same text there.
Yes.
Yeah.
There is no big difference. So also comma separate the file to create in using our application. It's very nice to listen to me and not to speak with others.
No, I'm just
It's
sorry.
not- it's not okay.
that because
It's
you,
not
did,
okay.
you didn't follow, Peja. Thing is that with your application, we tried in a field yesterday. Mirjana was there. You need to choose between 170, 100.
No, you don't.
No.
You
Okay,
don't.
then we
You-
don't
you
know.
put
No, well-
others and say use the same semicon or
Yeah.
notation as you use. I don't say you don't need to. Maybe this application is better. It's
No.
also
I would say that if you have something in the house, I would use the application in the house, 100%. So it's not a matter. We have not done anything still with the QGIS for our region as a test, but we have already, at least in our region, we have already filtered completely the habitat types, not just the list of habitat types, but also the locations across the territory. And we are going to create this tool for giving to our botanists in QGIS because we have nothing else to use. But if you have something, I would do it.
But then it's up to Tonya to get agreement with CIT team because and the botanist. It's not me who's gonna decide. You just go and talk regarding it, and then I would just like to know who is the one who is adding up new things in that MCAS.
You don't need to add.
Is
You
it-
can everything write in comment. In comment.
in this box other.
Yeah. It's
For any.
Yes, I know that, but it turned out okay. Then you can discuss with them. What do
Yeah,
you prefer?
I just suggest to compare all available solutions and to see what is the best.
Yeah, but I think it's a matter of discussing the content to put on the solution. The solution itself, the simplest, the better. So the QGIS, I actually, I like, but I don't want to say don't like. I like it. We are going to use it, but it's outside of your hands. If you want to do something else or something less, you can manage at a certain level. So if you invested time and money to have something on the house that can be used, I would go for that. But just one recommendation: we can adapt the QGIS, but to compare which is better, I think is not necessary. It's better to discuss. This is enough. That's good.
But it was just my intuition. Like if I go to that box other and then say this is the code for the habitat, then comma. This is the status one. This is and then on the comma. This is this 3. Then the comma and then I forgot which and then I need to count.
Yeah. When I went to the field,
confused, yeah.
when we did it in Turkey, at the end I read the code without commas, and I knew what does it mean because you are so used to do that we read A, B, C, 3, 4, 5, 6, 7, 7, 7, and I know what's that. This is a forest of Corylus avellana that is not age structure, the diameter of individuals is low, because you are so used to that, that is quite straight. And what you store at the end is a character separated by commas. It's very easy, transfer to everybody.
Yeah, I believe so. It sounds like it's.
And in the end of the comment, you can write a note after that.
Yeah.
Put the space and write everything
Whatever.
For yourself.
When you upload to some system, you can say to the system only storage as a save file the first 20 characters.
No,
and then the other two comment.
until the first space.
Yeah, first space, yeah.
Okay, so you use these phones, but you can also use the tablets, but tablets need to have the phone card.
No,
No?
no phone card.
You don't use phone card.
No,
The
nothing.
phone that Milena wants.
You just need the tiny smart Android device that has GPS, and
Okay.
basically that's it.
Okay, then it's up to you.
receiver
So.
Yeah, so agree.
When you come back, you need to connect to internet and send data to the servers, and that's.
Yeah, that's good.
So if you have a card.
Yeah.
It will be easy to send directly from the field.
Yeah, sure.
I mean, it's not much.
Yeah.
So we need to get to the office.
I would say that having IT people in the house, I would always use your own solution. In IS Cantabria, we got money for doing our own solution. At the end, we didn't do it because, well, another things. But if you have people in the house and technology, I would use that because it's in your house. Yeah.
Sorry, one question for Boris. Taking that we use the AcroSense application where you need to put in characters by hand, right?
Mhm.
How many different like
Combination.
around which number habitat types are there in Vojvodina that we will need?
About 140.
So we'll have a
we don't
list
know
in on
codes by
paper
heart.
and then go through and.
Yes, sir.
We don't know Eunice codes by heart.
Of course, we the field we gave to the bot. Well, in Turkey, we have the other option. We have the option that they click and they have a list.
Yes.
And we put like pitfalls in the middle.
To help.
But we needed to do that because we had no confidence on the button. So we preferred to give a click.
But if you send me to the field, it's going to be the same. You cannot have confidence in me being the botanist.
Well, that's another one.
If you write in a comment, I need to know that, or maybe I'll take.
No, but you can have one list and in a paper. I mean, you can have help for taking that decision. But of course, needs some kind of expertise and of course, not to make mistakes that can occur. You can make mistakes when just typing. And in this case, it's a list that appear and you click. Yeah. It's sorry, you were
mistake if you click.
You can make a mistake as well. Yeah, sure. I actually like the simplest the better, and it's much simpler having a block to write the code and the numbers from a view. If I have to select, I would go to for the simplest option that depending on QGIS, then changes maybe in the tool in 1 year or not. Well, then this is something very simple. And what we aim to do is something very simple. The code of the habitat type, I know the level 2 of all the habitat types and not all day in the field. So even though you have 140, when you go to one place, you more or less know which is the level 2, and then it's not 140, it's 20, 50 habitat types. But okay, you have to discuss about that. Yeah. And this does not mean that we can create that QGIS, that happens, and put there to allow you to discuss or whatever, but then you have that option that not everybody else have, to have IT people in the house to select a system solution, but it depends on you. The thing of this is to avoid having GPS collecting the points, and then one notebook to write down this GPS is the 4 point in the afternoon, and I want this code, and then I go to the GIS and manually, I don't know, you have to do that still. Okay. And that reduces many things and help reducing at many levels the uncertainty, because if we arrive to this place, this will be always a mixed forest. That's perfect. But if we go to a place like that, in the GPS accuracy, maybe we put the point in this grassland, but we move to other grassland that has some rublands of Calluna vulgaris there, and everything changes. So we are going to have the orthophoto. We are going to use the orthophoto to locate my point, and well, it's what we talked yesterday. Well, I don't want to go into detail because Jetse talked before me, but we have not to do this accuracy control only with the in situ data, because then we put together with all the predictors. And the most important one, controlling the quality of the data, because topography could be, climate is another thing, but soil and remote sensing have a lower spatial autocorrelation in terms that putting one location in one point and putting in another point would change everything in my further modeling. If you put one point here or you put it here, nothing happens in terms of climate, almost nothing happens in terms of topography slope, but everything can change in the remote sensing response and in the soil properties if we have that soil property map that Jetse told us before. So the in situ data need to be coupled to the remote sensing and all the spatial predictors to do what we call the data curation. Is that coupling, putting together the in situ information that once collected in the field. It's not important the good job you do in the field if then you are not putting together that information with the spatial predictors. This is the soil map. This is the pH or soil organic content. No, this is the pH of our region. You can see here the level of detail. It was validated. This is a correlative model. Then we have to run a mechanistic model for soil organic matter with Jetse and 2 PhDs from him of Wageningen, and we did a very great job. And then the promising thing when we finish this analysis is that when we combine the in situ information, the unique habitat types that we have with the soil properties, the correlation was perfect. So the sandy soils were mainly located in headlands, in headlands affected by fire, that resilient communities that become again headland after fire, and the higher amounts of organic matter were in the mature forest and so on. And well, it was very, very good result. And of course, it was the most important predictive layers in terms of biodiversity distribution across space. And of course, the remote sensing, I wanted to get into details, and I told us quite a lot about this, different satellites, different options. We talk only here about optical, multispectral optical applications of multispectral satellite imagery with different spectral, spatial, and temporal resolutions. But we have LiDAR, we have radar, spectrophotometer. I have not already voiced. We have LiDAR, we have spectral.
Do you need water?
The spectral resolution.
Bueno, okay,
Do you need water?
radar, is possible. We have passive imagery, we have active imagery, and of course we have drone and aerial photo that is there for being used. I eliminated the slides because I wanted 20 minutes and I have more. But in my PhD, I made a multi-scalar analysis of how these remote sensing sources, this is one slide of my PhD, allows you to understand what is going on at the landscape at different levels. For example, you can analyze fire recurrence and vegetation recovery after fire with remote sensing in 10 years, because if your area, as my area, is burned every single year, it's time enough 10 years, and the satellite imagery grain side is enough. But if you want to model, like these two pictures, forex expansion through time, you need not 2 years, 10 years, you need 50 years, and you need aerial photo from the past to now and so on. But all that information, whatever was the origin, the resolution, spatial resolution, or whatever, what we need to do is to couple the in situ information with the remote sensing. And with the remote sensing, with the powerfulness that I explained, and with the efficiency that Gonzalo allowed us to see that we can manage, we don't need one single image. That was like the first step. If you start to work with remote sensing, I think it's enough. If you spend your effort in learning how to correct the image and use the NDVI of the point in the year, the point in time, with the maximum solar angle in summer for avoiding clouds and so on. That's the beginning, that's good. But then the powerfulness is this, that curve. That curve is what we call the land surface reflectance, but I like more the name of spectrophenology. It's like the phenology of vegetation by, sorry, this is not good, it's not bad number, it's time. But these different years, these are months, 0 for 50 months and 0 for 50 months. So these curves are the phenology of vegetation. So with that, it's amazing. We are applying artificial intelligence here, Fourier analysis to decompose the information that you can get from that curves. We collaborate with companies, one of the most powerful companies, I would say, in Europe, because they are leading the biggest project in Copernicus climate for analyzing this kind of thing. So we collaborate with these people to come on, extract me whatever from these curves for getting indicators for what is going on with this kind of vegetation types. So this is an stable forest. It's very easy to see. We have no leaves, I lose the leaves, I gain leaves, lose the leaves, gain leaves. And it's a small trend. So this is a young forest that is getting maturity through time, but not disturbance at all. This is a grassland also, smaller values. Here we are at around 0.8. Here we are, the average value is 0.05. That nothing happens neither. It's a grassland that is not being used. So it's getting a biomass and so on. And this is a recovery after fire. You can see here in the month 0, that NDVI is 0. And after NDVI, we have a sprouting of vegetation or seedling of grasslands in that burned area, quite high until NDVI of value 0.8. Then that annual species disappear and start to appear again the shrublands or perennial species. That gives a value of NDVI increasing, but with low phenology. So a botany, if you understand the community, you can understand the trends. And what we do is to put together and reject any single point of those communities that is not fulfilling this criteria. So I cannot get a point in shrubland and in forest that has this behavior or this behavior. Well, I am simplifying things, but that's more or less the idea. This is a very simple example. This is a productive grassland. We talked about this yesterday. Productive grassland and annual alpine grassland. What happens through the year to this grassland? Nothing. It's the flat curve of the 12 months of the year. But what happens in a managed grassland of lowlands? Because you need that grass for grazing, for mowing. So what happens is in late spring, you have the maximum of biomass and so on. Maybe this is quite simple, but just to highlight that we need to couple what is going in the field and what is going with the remote sensing. And all that things that are curves, are draws, what we do is to transfer into numbers, what is called spectrophenological metrics. And that spectrophenological metrics, when are obtained after expert criteria and following a pipeline of collecting data in the field, put together with the remote sensing, agree with the experts that the data is correct, agree with the stakeholders that the output of that analysis is useful. That's, as EuropaBond called, a workflow of defining an essential biodiversity variable. So this is an essential biodiversity variable in such a way that it gives you solutions for something, and it was obtained following a structured methodology. It's not just I do what I want, I go to the field. So this is in the EuropaBond workflows are understood that that translational ecology that I told before, something that is agreed for a specific objective. We were collaborating with the colleagues of Vito in EuropaBond to define one EVB, essential relative variable, that is called the horizontal extent of UNI's habitat types. That's the EVB. It's just the habitat mapping. We put a name because we agreed a way of working that ended up with a map of the state of the habitat type. Okay. And well, this is a simplified thing, simplified view of everything. You have, these are our golden points in the region of Cantabria that we collected for working with Nature 2000. So these are quite a lot of points, but each point was curated there with this, well, that example that we went into every single point, defined a number of metrics, and decided this is good. This is very good. We are doing the same now in the whole Cantabrian Montes, exactly the same, with around 80,000, 10,000 points, curating the points for assuring that we, using this curve, so this is the curve of different forests, beech forest, oak forest, shrublands, and so on. So by doing this, we assure that the point is correct. And of course, we are not doing always with Sentinel. Maybe you have to use Landsat if one of my properties need to be assessed for a long term. One of the variables that give very interesting information is what we call in ecology stability, the forest stability or whatever, is that nothing happens in one pixel during the last 25 years. But for doing that, we cannot use Sentinel, we have to use Landsat. And the simple indicator that we get is stability yes or stability no. But we need to assess that for 25 years. So different indicators that come from this kind of curves, using different satellite imagery, Landsat, very high resolution, Sentinel, aerial imagery, drones for sure. So at the end, we get these metrics for the curves. We get these metrics that are start of season, end of season, maximum, and this is mathematics. But when we put together these mathematics, this remote sensing, the experts field, agreed solutions, we have the workflows of essential biodiversity variables that at the end of the day are indicators, well structures to give us responses following structured methodologies. And that's EVB. Again, it's another way of putting names to things that sounds very cool. The EVBs of GeoBond is much better than indicators of spectrophenology of habitat types, agreed with experts that is the same, but with a cool name. And all this again is very complex. And this is going much more far away than the far away we arrive with the explanation of Anna, remote sensing. Here appear the botanists, went to the field and defined the communities. But again, everything can be summarized in this kind of beautiful, horrible things that Google Earth Engine, that we can write code for doing everything. And our dream now, our work as a group at IMIB is to create a pipeline in Google Earth Engine that does everything. Since not going to the field, that maybe in 10 years we have the robots. But once you go to the field, once you do the job that we're going to do, when we started to work with the rangers in our region, they told us, there were a couple of guys that told us, I don't like it, because you are going to replace the botanists. So we, the botanists, are unuseful already, or what happens here? And we always try to explain, no, that wall, these are complementary tools. In fact, the only person that will never be outside of the equation will be in this case, the botanist, talking about the animal species, the specialists in the field about species. But artificial intelligence, I don't know what you think about that, you are IT and remote sensing, will occupy our place year after year, a little bit more. But the technology, not reality in the field, that's my view. So we can code all that things of spectrophenology and so on into Google Earth Engine, and we call it, in fact, the PhD of Gonzalo that started and then stopped, and let's see afterwards. What the first chapter of the PhD of Gonzalo was compare what can we do with Google Earth Engine doing our best, and what can we do as homemade workers of data doing our best, to try to characterize the uncertainty of the decisions that you can take with Google Earth Engine and the decisions that you can take doing things manually. Now we are trying to move that idea into Google Earth Engine again. We have working with that girl I told you, Beatriz Cazorla, from the University of Granada, that she is really expert in the tool, and we want to press and push quite a lot to the maximum the code of Google Earth Engine to do almost everything from data curation up to the solutions to the stakeholders, including reports, including the web page that we are preparing with the people of Granada, to allow the end users, even with no expertise at all, to make consultations in Google Earth Engine and give the specific answers they need about whatever. I'm finishing. The thing of this is, well, I'm finishing, well, yeah. The start of everything again is we move to the field, into Google Earth Engine, but again, the situation is that we need the data collection in the field. This will never be moved. This data collection needs to be accurate to translate that in situ information to satellite imagery. So we run our models independently of how, using Google Earth Engine, using R or whatever. And this is our seminal paper that was our bridge to EuropaPON and many other things, on which we only define this theoretically, that how mapping habitat types and biodiversity of vegetation by putting together in situ data, environmental factors, and remote sensing. This is what Borja presented in the previous seminar, is the advance of that. And the only difference, and I want to go into details on that, the only difference between this and this is that hierarchical control on which we aim first having land use, land cover maps agreed that are good enough for moving afterwards only within the formation, within the land use, land cover, moving into the habitat types, for avoiding that thing that has no sense of mapping directly habitats and make commission across the territory. And what we get at the end is a raster map that can be transformed into a vector layer of habitat types, and we can do whatever. What we can do for transferring, as we record it now, which is the difference between modeling and mapping. What we need to do is, which are the needs that we are going to fulfill with our maps. So this is like, ¿cómo traducir célula madre? Because hablamos de hacer en español la presentación. Yeah, so it's like that cells that can be whatever. When we are born, we have that cells that afterwards, stem cells. Okay, so these models, not the maps, the models are like stem cells themselves that we can transform into wherever we need. Of course, into wherever we want, but in this case, would be like infinitive of solutions. Because if we know what the end user is expecting from our map, we will define that solution for that map. That's what Copernicus is doing with the Copernicus CLC Plus, Copernicus Land Cover Plus. They call backbone to the CLC Plus, backbone, and then they have instances for different European policies. Instance of LULUCF, instance of Nature 2000, instance of whatever. It's more or less the same. Just a brief example, I'm already finishing. So one piece of territory that looks through the window, that map that we saw in the beginning with a picture, we show now with autophoto. And this is the map, the official map that we have in Spain, the forestry map. So that lines are more or less good in some places, but come on, others is like, well, a little bit arbitrary. But if we focus on I missed one slide. If we focus in this small patch of the territory, the National Forestry Inventory is telling us, I don't know why I have not that slide, is 65% of tree fraction cover. So 65% of this patch is forest. And within that 65%, we have 45 of beech forest, 35 of oak forest, and I think that 10% of Ilex aquifolium and other species. If we apply our models, we can know where we have the Betula forest. So this is the patch, and Betula is in the whiter pixels that we have there. And then oak is in the whiter pixels that we have there. I don't mind if I have no Betula here. I don't mind. I am always focusing in this, only focusing in this patch. I don't mind if the prediction is telling me here that I have probability of forest because I have the mass of forest. I don't mind. I only focus on that. And I know that oak is around here, Betula is around here, Ilex is around there, and we went to the field, to this location, and we found the Ilex aquifolium in small population. And at the end, that's a model, and we have to validate. So as we discussed yesterday, for real validation, we have to have another botanist, another team of botanists going to the field parallelly to the botanists that are going to take the training data for the modeling of habitat mapping. That's the real validation. We are not going to do that. What we do is to bootstrap with different techniques, the information, the calibration data set, and the reference data set for getting estimates, different accuracy estimates that are telling us which categories are being confounded, which with other categories. And in the second round of the habitat mapping, that in Sonata will be the next year, we will spend the effort in refining the errors, not in fulfilling the whole objective. Okay, that was one option. We doing our best this year, and the next year to spend the effort in eliminating these errors, omission and commission. That's what we did in Turkey. We were modeling the whole Central Anatolia region, is half Spain. And what we got at the end, following this process, this workflow, this pipeline, is the identification in the whole Central Anatolia of the main habitat types at the units level that we transfer afterwards to Annex 1 of the directive for identifying the nature creating from this using Marsan, systematic conservation planning. This is quite similar to the spatial tool that Vito is creating for Sonata. We made an application of Marsan into our code that allow us to do many, many interesting things. We applied in Turkey. And at the end, the most important thing is that this allow us eliminating that breach. So we have not two different worlds now. We have vegetation data and remote sensing talking together the same language to achieve our objectives. And that was a figure that we created in Turkey to combine as stakeholders. And at the end, I was invited to the wedding of the daughter of one of that people in the ministry. So we are friends already. We put this number that were more or less real. So what we can do is the same that Jetse told us how to create typical habitat mapping only using field work. So it's impossible. 7 million euro only going to the field for covering the information that we needed. And by modeling more green phases, because you improve a little bit more everything, but always with the combination of both. not the what, the combination. So remote sensing and in situ data are complementary tools. They are not excluding one and the other. And 20 minutes, we're at 20 minutes, but I have exercises to go steadily into each step to do the hands-on. You have the exercises there. I don't mind. We have time enough. We can just go through the GIS, but we will have to work this hands-on when collecting the real in situ data from SONATA. For doing this, this is the summary of the hands-on, the exercise that I have. First, data collection in red, because we're not going to do here. They are going to do. They collect the data in the field by assessing. First, that's what we did yesterday. We have to create a document. First, assessing the previous maps, then go into the field with expert knowledge to collect that information. Then we put these three words they are an explanation of the main issues. With that data, what we do first is the data cleaning. So this word of data cleaning is the whole workshop of today, is eliminating the outliers. We don't want to maintain, even though in the field they are correct. So we go to the field and identify a forest. And in the middle of a forest, I have a forest, no uncertainty since at the level of in situ data. But when we put that forest in the time series of remote sensing, because I don't know what, the data for that point is 0 NDVI during the whole time series. So in 2 years or 4 years of analysis or whatever, I have to eliminate that point. I don't mind if that point is correct or not. We have to eliminate. In that Google Earth Engine comprehensive script that we are creating in the group, we created a subtool from this that moves that point to the nearby location that fulfills the criteria once the location is discarded. So, but we can optimize this. But cleaning is eliminating the outliers. In Turkey, that's in the exercise. In Turkey, we started with 2,200 points, and this step eliminated around more or less 150,000 approximately. Half of the points were eliminated here. So it means that the information was medium quality, so we're refined. Then we have the data filtering. The botanists in Turkey, that's what we were talking yesterday, we told them you have to collect information for the whole territory. So they arrive to one forest patch, and say, okay, this is a forest, and this, 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 and put like 20 points in the same patch. So that has no sense. That increases the spatial autocorrelation. So we then eliminate the spatial autocorrelation in space and time. Okay, so we avoid having one point and 100 meters far away, another point, and then another point, and then another point. And we avoid having 1 point, 1 year, and the same year, another point in the same location. We don't want that. We eliminate the data by filtering information. And finally, this is the more technical one with a lot of new tools coming up with the new technologies of time series, is data refining. Data refining is once the information has not outliers in terms of the indicators, not only NDVI, wherever essential biodiversity variable that we can define for each habitat type, we can include in the cleaning for avoiding having a connection of 1 point with remote sensing that is not representative of that habitat type. So different indicators that we have to identify here in SONATA for putting together for modeling, but first for data curation. The good thing is that once you have created the data with remote sensing, you know that modeling is going to work like a Ferrari. Nothing happens. There is no problem at all because you clean every inconsistency in the beginning. And this is the most tricky one because this is like place the geostatistical tools. So this is a play of try and error. So we run models, but not for having results. We run models for improving the data set. So this is a way of improving different tools. Now we are working in the Copernicus project. We are working with an IT company with our partners in that project, and we are trying to automatize everything by running Python scripts and R scripts and so on. But at the end of the day, that strange word that we can automatize this are data curation after the collection. It's cleaning, refining, and and filtering. And with that, we end up with the workshop. If you want to go into the data, we can or not. But one comment only about the mock course. Have you, all of you, heard about the mock course of Sonata?
No.
No?
Not at all of them yet.
Okay. Do you know what is a mock course? Massive open outline course. So they are beautiful tools for once Sonata finishes. Hopefully, Sonata was the starting point in Serbia to map nature, infrastructure, skills, and whatever. But the mock courses are massive open online courses that keeps the essential thing of one project or whatever to disentangle the whole project into the hot topics of the project that match more or less the working packages. No, well, Anna recorded now in the social networks, so you can see afterwards. So that pills of knowledge. So let's explain it better. Is it okay?
Yeah.
It's okay, like the explanation and
Yeah, no, it's perfect. I mean, it's just to highlight. I mean, there's going to be a very well concentrated message of each of the aspects that are going to be developed within the project. So in order to reach the wider the audience, but also like to serve as an example of well, to refresh our minds of what's going on and take home messages, basically.
And we were conducting that Alice project that I have mentioned many times, or an interreg project that Anna and me were coordinating for 5 years. And it was a mock course in Alice project, and it was nice, but we did it at the end. And it also was that moment when we leave the group and so on. But anyway, here in Sonata, our dream, and I think the things well done, is that the mock will accompany Sonata since the very beginning. As soon as we finish one task, we will record the mock of that task. For example, I would say we will have to have a mock of field data collection. So when we finish the field data collection, you can share one lesson. It's around 1 to 2 minutes recording. So you can share the lesson of field data collection. And it's just summarize what we agreed to do as a best solution for field data collection. Another mock we want to have about in situ data refining, and we will record another small course. So at the end of the day, we will have everything in Sonata summarized in that courses with an index.
Hold on.
Yeah.
I mean, the MOOC is going to be the whole thing, but there are going to be like different sections. Every section is going to recollect the whole bunch of activities. So it's not that they are going to be separate, but under the same umbrella, there are going to be different topics tackled.
And what we did, and what you can do with the mock afterwards in BioSense or whoever who manages the dissemination of the course, you can offer the whole course, like a Sonata collection of everything. But maybe there are some people only interested in remote sensing habitat mapping or only interested in stakeholder engagement. So you can offer small like titles, recognition to the people attending the mock for having like a Sonata recognizing of you have done the mock of habitat mapping, in situ data collection. So you can split as you want and open the audience that you can reach with the mock. In Trasmares, one of the projects that we participated in the project, well organized with the mock, there are thousands of people attending. We receive emails from people from Africa, from South America. I saw your mock in Trasmares or in Alice. I would like to collaborate with you because I am doing the PhD and so on. So it's very, very, very easy to get audience because you are giving the pills of something that afterwards has behind quite a lot of job, made papers, and so on. So we prepared today one example of a mock, just in case you want to record or whatever, because we think, and we talked to Tiana Maya, that would be a good idea to have like a spot of record here in Novi Sad, because all of us will come to Novi Sad one day and after another time. So every occasion that somebody arrives here can record the mock from the partners from outside and also from your side. And the last, it's not important to record more lessons that we finally are going to put on the mock, because that's, as we did with her, that's good for social networks and dissemination, beyond the mock and so on. It's just, and also the mock has a structure. You as an author of one task, we write down in a doc file and a script. And the mock, you read the script. It's not something to invent. It's just you read, it's like an abstract, and you read the abstract with a prompt or with a laptop in front of your eyes and a camera here, and you read and you can try a little bit, and you are not going to forgive any keywords. And
Yeah, but I open it, okay, let's just talk about
yeah.
it.
So it's a matter, this is the list of all the models that we suggest for Sonata, and it's been under review, no? Claire? So we have to agree. We are not in a hurry because, I mean, this is for the end of the project, but it would be nice to agree as soon as possible to know which lesson and who is going to give that lesson, one or more people.
Actually,
Yeah.
we kind of were aiming of having, or at least the first a few number of lessons to have the persons and the topics done by the end of February.
Yeah.
Okay.
And then the later ones can come.
Yeah.
End of February, this year.
Yes.
It's tomorrow.
Decide on who will going to do it, not actually recording. Yes.
But then you do have the list, there is in VP5 folder, everyone can find it there. There is this revised list. The Vito team already did give their feedback. Maria and Maya work it out. We do have a name. That's why she said, like, it's almost done. It's just a thing that Are you?
Yeah, this will be, the mock will be an alive list for sure, that we will improve, that we will change. But it's nice to have like a scheme and respect that scheme for once one task is ended up, just record the mock and it's done. So at the end of the course, at the project, as we suffer in Alice, you cannot remember details about the in situ data collection that you did if you are in the third year writing the report of nature-based solution definition. So it's much better to end up the task and record the mock. And yeah, and it's done. I had another version, shorter, to spend time in the exercises, but I know that you are tired, and I preferred finally to open this one to go through that philosophical theme of in situ data curation. And as I told, it would be a very good idea when you finish the first year of the in situ data collection, maybe September or more or less, or whatever, to do a hackathon for running this kind of analysis all together. So everybody that wants, or whatever, to be just touching the data on the computer with the scripts necessary, with the application necessary for going all together since the raw data from in situ data to the final data that will be used for final habitat mapping. It depends on you. We can open the exercises, I don't mind, or we can just give it up and discuss questions or whatever as you want. You have the decision, I don't mind. It's so long, quite a lot of things, but
yeah, it was like the
data is there. What you have, just
it's a Thursday, come on.
Yeah, for that reason. As I just show you the data, it's very, very simple what I put here. Well, this is a GIS scene of the study area in middle of Turkey, but just show you the data. So the data, what has, okay, come on here. What I put in the data, that is what.
This is session number 3.
This is session number 3. Yeah. What we have is what we have been discussing now. Training, there is a number of folders that have field points collected in the area, that have the study area at different levels, talking about land use, land cover, roads, cities, the target areas that we visited for collecting data, and one grid that we always use, a grid for controlling how in situ data is collected and avoiding spatial bias. We always say that this grid, I will open just the grid, if this you want to open. So we have this kind of grid. just for not making it easier in a small area. And this 1 kilometer grid square is selected for avoiding spatial bias when collecting in situ data. I think I have the field points already here. So these habitat types are distributed across the entire target areas that we want to map. Why we have not points in these areas? Because these are agricultural areas that we discarded because of Corinne. I think I should have target. Well, come on, I think I had it. I'm going to change to charge only then uncover. Training, static area. For now, my computer. Okay, Corinne uncover. I don't know what happens with my computer in Spain. I cannot connect. I can do nothing almost. No, I don't want you. I want the target. Okay, target. I want you neither. So mask, this one. We identified from Corinne, as we did yesterday. We identified from Corinne, if it wants to upload. Okay. These are the target areas on which we want to work. Areas outside of this, they are called mask out. These areas were masked because they are agricultural areas, urban areas, and so on. It wants to. Okay. So I don't want to work in any area that was in that color. But in all the other areas, the botanists were launched to sample the different habitat types. Okay, so we put the habitat types in the natural areas and so on. So we have the training data collected in that areas, we put on the table. Then we have predictors. When we started to work in this big area, I was talking with Tiana in the lunchtime, we wanted to work with Landsat and Sentinel, 10 meters, 20 meters, 30 meters. It was a nightmare. And we started to make modeling tries and so on at 120 meters. And we had information about bioclimatic variables, topographical variables, a digitalization model, remote sensing, soil grid information, and so on. Then we made the same exercise. Now we run the analysis again, sorry. The same analysis, come on, with at 30 meters. Same variables at 30 meters. That variables from remote sensing are a combination of Sentinel and Landsat, doing our best for creating mosaics at 30 meters and getting estimates with no gaps, because the area was so huge that covering everything was a nightmare. This project was done in 2018. We had not Google Earth Engine then. We had to run everything in Java. For avoiding R was not able to work this, so we had to move to Java and so on. So well, predictors at different levels. Then we started to model it. We use species distribution models. We first used Maxent because we wanted to use Java, and it's programmed in Java. It was very easy. But there were some people there working in species distribution models, and they wanted to make ensembles of different algorithms. So we moved to Biomod 2. We moved to SDM. I give you here some documentation about the three approaches. Maxent is a single standalone algorithm that uses maximum entropy. Then we have Biomod 2 that some of you know suffering it, as Tiana. And then I love the SDM approach. This is not the concept SDM. It's an approach done by Babak Naimi and Miguel Araujo, published in Ecography already 8 years ago. There is an algorithm very flexible, very good to run analysis, very well documented, but it's not updated. Biomod, it was updated last year. It's a nightmare again to update the script, but at least you know that there are people behind supporting the algorithm. Well, so training data curated, predictors data curated at different scales, putting together, as I have been explaining it, avoiding that any inconsistency between both. This is what I've been done in the last months for that paper that we want to publish for the project in Turkey. And we achieved an accuracy of 97% at the land use land cover model with 25,000 points. I cannot be here the matrix if you want, I am not invented. It was a really would surprise to achieve that level of accuracy, and it's tricky. And I'm going to tell one story that Anna knows. When working in the ALICE project, we contacted with a company of French people that are very high level working in land use land cover. And in that project, somebody decided that we are not going to create the land use land cover maps, but that company was going to create the land use land cover map. So that's good. And the accuracy of the maps were 99%. 99. And we thought, come on.
The 9999.
It was like almost perfect. These guys are really good. So what happened, and this the remote sensing people will understand. So getting an accuracy of 99% in land use land cover. Sorry?
It's wrong. Yes.
Well, in the beginning, you think these famous people is like, wow, it's amazing. But it's not a criticism, just pure criticism. It has an explanation.
It is criticism.
No,
It
it is
doesn't
not.
matter.
It's the criticism of the practice. What occurred is that they calibrate the models and they validated the models with 150 points, located only in the middle of the biggest patches of each land cover type. So imagine a patch of forest of 1,000 hectares. You have 1 point in the middle. Then you have a big grassland patch on a meadow of many hectares. You have 1 point in the middle. And they use for calibration, that's good. They use that information, that's good, for calibrating AI algorithms for land use land cover. And in France, the 99% was true, was good. The map was amazing, really, the level of detail. But what happened in Spain is that they use level 2 imagery without topographic correction. So the reflectance in the slope was very different, and the map was a mess. Everything was coniferous forest in our mountains, and we have no coniferous forest in our mountains. So the map was, come on, this is not good. There was not a connection between the in situ data collected, the amount, distribution, and the remote sensing, and so on. So we took into account all the things. I finished. Yeah, I finished. So models,
Or we kill you.
and finally the maps. Just only that 2 folders.
Okay.
Web mapping, web map deformations. These are the first level hierarchical model on which we reach accuracies of 90%.
Those are some results inside.
And yeah, you have the results inside. Formations, and you have the habitats, which go deeper into each formation for mapping the distribution of the habitat type. And that's all. So we are going, that's I think is very good, to do this with Sonata in some kind of hackathon or not, maybe a workshop showing the results when you end up with the field campaigns. And that's
Yep. Okay. Yeah.